group of great people behind the work that you're going to see today. So what I'd like to start with really is just kind of an introduction and overview of the results. So the introduction part maybe introduces you to fiber optics, how the technology works, what it is, and then an overview of just the kind of a broad overview of what we've collected in the last year. Okay, so how do I move my screen? There we go. So there's an acknowledgement slide. So, you know, there's a lot of great funding from the DOE behind this work that we're doing here. There's we always want to acknowledge the stakeholders, you know, in the region where we're working, in the county, and the state, and the state representatives here. There are many people have supported Neubrex's operations in the field. Some are here today: John McLennan, not McLennan, McLennan, Joe Moore, Kevin England, Leroy, Alan, Garth, Monty, and then you know, other people that are on the research side that have supported. And I don't want to overlook the guys that are the guys and the gals that actually work on the frac, drilling, water management crews, and the HSE people who keep us safe out in the field. So just a little bit about Neubrex. Neubrex is not any kind of a newcomer to fiber optics. The people that founded Neubrex Energy or Neubrex Fiber Optics in Japan had been doing R&D work in fiber optics since the early 1980s. And in 2001, they spun out of Mitsubishi Corporation to form Neubrex. And they started kind of looking at all the elements that are important in fiber optic data acquisition, data processing, and so forth. So that really starts back here at looking at the glass. The glass is really the sensor. The glass strands are what get put into the fiber optic cables, and those would do all the sensing. And then the coatings and the cable construction, and then building the electro-optical interrogator units that actually send the light down these strands of glass and then take the backscattered energy and make sense out of it, strain and temperature and acoustics, and building that all into a integrated system that actually works in the field, take it to the site for site tests. And then in the end, my job is to generate value from these systems and communicate those results to groups such as yourself. So Neubrex is quite a mature company in this sector. Okay, so Utah Forge fiber optic diagnostic drivers. What really drives what we're trying to achieve here? What's the value and what are the objectives? So let me just start on this little blue circle here. You know, fiber optics was chosen as a potential measurement technique here because fiber has the great ability to survive in high temperatures and high pressures. There's no elastomers or metal or moving parts in fiber optic sensors. So, you know, the fiber optic sensor is the glass itself that's encased in a cable. So it has the ability to sustain itself under harsh downhole conditions. We like to say it has long life for downhole. Most of the time that's true. You know, we've seen fiber optic downhole that have lasted for decades, and then sometimes we've seen fiber optic cables give way after a few months of use. It really depends on the conditions of that individual well. You know, fiber optics is great because it provides for reporting consistency, you know, over multiple evolutions of monitoring. It's essentially maintenance free. Once you get it in the hole behind pipes cemented in, it's in the hole. You don't do any maintenance, at least downhole. You can do maintenance when it comes up out of the hole and you have access to some junction box fibers, but effectively it's a maintenance-free sensing system. And it really, because of these characteristics, it supports a lot of time-lapse change detection, which is very important in oil and gas and geothermal and CCS type of applications. A purpose of the Forge project and its use of fiber optics in this kind of venture is to demonstrate the full cost value proposition. What value can fiber optic diagnostics bring to the objectives of the overall program? And the other nice thing I just wanted to point out is about fiber optics is that it meets multiple diagnostic measurement objectives because you have one fiber optic cable that runs downhole with these different fiber strands in it, but you can hook different instruments up to those same fibers. And you can measure acoustics and temperature and strain change and strain change rate. So it's really versatile in that respect. Okay, so just kind of a little close the loop kind of diagram here in terms of timing and the fiber optic aspects at the Forge project. So in July 2023, really a couple of fiber optic cables were installed into the 16B well. There was what we call the UT shell cable, and then there was the Silixa cable. What I'm going to be talking about today are measurements that have been made on the UT shell cable through the last year and a half or so. So the first real field operation was to actually, strap or clamp that fiber optic cable to casing to the 7-inch as it was ran in hole, pump cement, and watch those operations. Run in hole, check the health as we were running in the hole of the fiber, and then pump cement, watch that operation dynamically. And then after that, so that was in June, July of last year, 2023. Right after cement pumping and curing, then there was a short crosswell circulation test that was done in July of 2023. Neubrex monitored that. That was followed up in the spring of 2024. I got a typo here. April, May 2024, we did both crosswell and in-well frac monitoring. So that means we were fracking on 16A. We were monitoring at 16B fiber. And when we fracked the 16B well, we monitored that frac in well in the 16B. And then there was a short circulation test done after this frac monitoring, about a 9-hour frac, real short. And then in August, we came back for an extended circulation. This was Forge's 30-day circulation period. I will note that we got about half of that circulation period. I think we got about 10 days out of the total 30 days because we lost the fiber below about 4,200 feet in a fiber rig. Okay, just another way to kind of look at this type of the application of fiber optics at Forge. If you look at this kind of this pyramid here, it's communicating the same thing. We started out in 2023 with watching the cable installation and cement monitoring. We followed that up in right afterwards with a crosswell flow test, number 1. And I will say that what's interesting about that test, which is different than any other flow test, is that we didn't, the 16A well was not fracked after the 16B well was cemented in. But the 16A well had been fracked in 2022, the first 3 stages of that well bore. So a small circulation test was done on the 16A well using the original stimulation clusters in the A, and we monitored what was happening at the 16B well. And then subsequent to that, like I said, in the spring of 2024, April, May period, we came in, we monitored the A frac, the B frac, and a crosswell flow test. And then in August of this year, just last month, we came in for an extended crosswell flow test. So all of these, we call these evolutions. In our company, each one of the times we deploy to the field and use these things, we call these an evolution. And each one of these black boxes represent a single evolution that we were involved in. Okay, just some basics here. I made some pictures. I'll go into this. There's first principles involved here that relate to optical physics. So the thing about optical physics is the most important thing to know is that different wavelengths of light that are pumped down a fiber, you pump down certain wavelengths of light, you get backscattered energy, backscattered light that hits an optical plate or receiver. And these different wavelengths that you receive back have names to them from the physicists that discovered their uses over the last couple centuries. For instance, Rayleigh and Brilliant and Raman. And these different wavelengths are sensitive to different changes in the optical glass under temperature changes or under strain changes or under vibration, small molecular scale vibration. A fascinating science, all based on optical physics. Another, fundamental aspect of our work is that the fibers got to get in the hole. So this is just a picture of a 7-inch casing string, or this might be 5.5 in this particular picture, where the guys up on the rig floor have the fiber. The fiber is actually running on the outside of pipe here, and it's clamped to the outside of pipe with these mid-joint clamps, runs over these centralizers, goes to there's a coupling in here, casing coupling. So there's a crossover type of device that gets the fiber over the coupling and protects it, and so on. So there's a whole know-how that involves actually installing fiber into the well. And in this particular work at Forge, Baker Hughes and Alan Reynolds were intimately involved in getting this fiber optic cable installed into the 16B well. Now we talk about the, can I move this thing out of the way here?
So grab it on the top.
Yeah.
And just
slide it down, maybe right there. Okay. So this is just a cross section of the fiber optic cable that's installed in the Forge well. So it's called a flat pack, and it has a standard TEF, or tubing encapsulated fiber optic bundle. It has a structural member, like a braided steel rope that runs down the middle. It's called a bumper cable. And then we also have a DSS, distributed strain sensing fiber, which is more sensitive to the strain, which we're very interested in this kind of a project. So there's, this cable was designed by the UT, Shell, and Forge group to make sure that, and this was also a high temperature cable. So the fibers and the materials used to build this cable can withstand up to 250 degrees Celsius. So in geothermal work, you need to take into account the temperatures and pressures in which you're going to be working. And of course, this is just a picture of the rigs when they were working up on the job. There's a lot of site operations, so it looks like a regular kind of drilling rig site operation type of situation in geothermal. Okay, summary. I'll just kind of summarize real quick here. The big idea is that fiber optics is a great tool because it provides scalable diagnostics or versatile diagnostics. In my opinion, at economic cost value proposition, because the cost isn't nothing. There is cost in procuring the materials, installing, doing the acquisitions, and so forth. But the data is very valuable. So there's a good cost value proposition. Relative to many other types of diagnostic systems that you run in harsh environments, fiber offers long-term reliability architecture. And another beauty of this tool is that, once the fiber is down hole and it survives, that type of technology doesn't change much. But the surface technology, the interrogator units, and what we can do in data processing and so forth evolves over time. So once the fiber's in the hole, you could take advantage of evolving technology on the surface. Key takeaways in this project: it's been a versatile tool. We can relate the diagnostics to long cycle needs on these types of projects, which have multiple evolutions to those things. And the use of this, or the application, multifunctional, people with different skill sets are needed to define what type of measurements should be made to solve certain problem. And success really requires full cycle planning. It's like in any major project. You need to start out with a good team that knows what they're going to be doing, and then design a system that's going to meet those needs over the long term. Okay, what can be measured? So with fiber optics, there are ways to get to delta P, delta pressure. It's not direct, it's indirect, but delta P over delta time. And I should say delta depth, right? Delta Z. Delta temperature as a function of time and as a function of depth. Delta epsilon. In our world, we call strain change epsilon. So delta epsilon over delta T and over depth. All these are measured in depth and against time also. We can measure seismic attributes. We can measure seismic with fiber. You can shoot vertical seismic profiles and get images around well bores. You can also collect DAS microseismic data, which is a seismic attribute. And you can measure induced seismicity with these things because the fiber can act as a seismic sensing instrument. So there's a lot of evidence for what I'm saying here. That evidence comes from work we've done here at Forge. We levered a lot of experience that we have in oil and gas to kind of do the work here. Forge provides at least one critical use case as evidence that fiber has value in EGS. And here we see that the engineering needs mesh with the optical physics first principles. Okay, so I'm not going to go delve into this too long. I think everybody here probably knows the well bore geometries. That's true, right? I mean, you've got your injector. These are 65-degree slant wells, injector, producer. There's a couple of vertical monitor wells that have been there for a while and were used in some of the initial work. Let me just say that the fiber optic cable, of course, is installed in this upper well, the red well. The fiber's on pipe, cemented in place. It contains 2 single-mode fibers and 1 multi-mode fiber. That's important because different interrogator units or measurement techniques take advantage of either single-mode or multi-mode. These interrogator units are connected to the fibers at the surface through a junction box. There's a wellhead exit of the fibers. They come into a junction box, and then we connect into the fibers in the junction box. And then the interrogator units that we use actually pump controlled laser pulses at high rates down these fibers. Laser pulses are chirp. And then we record the backscattered energy that comes back, and we convert that backscattered energy into measurands that are important to us as engineers, such as delta epsilon, delta temperature, delta, vibrations, or delta acoustics. So all of this stuff is based on this setup here at Forge. I've already talked about this. This is kind of the equipment used in installation. I've already talked about these guys installing the thing. These are important people in any job. There's hangers, casing hangers that allows you to feed through the fiber optic cable up out of the well into the cellar of the well, and then out through there's wellhead exits in the iron on the wellhead. Just a picture of centralizers and crossovers and fiber protectors. I don't think you can see it, but this is the wellhead exit right here. So the fiber's inside of the cellar of inside the wellhead, and then it comes out through pressure controlled autoclaves so that we can get to those fibers and then bring those into a junction box. I've already talked about the cross section here, so I'm going to skip over that. Here's a close-up picture of the centralizers and the cross-coupling crossovers. The mid-joint crossover protectors look like this. They just don't have this middle piece here. So all of these things are kind of laced on every joint of casing as you run the fiber in whole, so that the fiber optic cable stays strapped to the casing string and becomes integral to the wellbore system. Because once you cement in, the fiber is effectively coupled to the formation at that point. Okay, so there takes some expertise. This is one of my fiber optic techs out here. So once you get the fiber up out of the hole through a junction box, you use specialized equipment that we have. This is a fusion splicer. So this allows us to basically, fusion splice or melt the glass together so that we're now connected to the wellbore. So that this melts the glass and fusion splices the cores of the glass together. This is what the inside of our world looks like when we're on a job. So we call this our DAC unit. These are data acquisition units where we put our interrogator units. These white boxes are the interrogator units that both launch laser light and receive laser light pulses back, and then do a little bit of processing in here before it's sent over to a main CPU unit. And the important thing about this system when you're on a job is that this is real time. When there's a job going on, when you're pumping a frac or watching a circulation test, this stuff with the compute power we have, you can watch what's occurring real time and communicate with, the pumping crews, with the command center, and so on and so forth. So this is a data acquisition. This is a Neubrex data acquisition unit. This is, I talked about the junction boxes. So when the well fibers come out of the hole, they usually run them over to a JB. We call them a JB junction box. And then it's this junction box that we connect our extension fibers into and allows us to connect this equipment here to downhole. And this is just what the outside of one of these DAC unit looks like. So this is just a very heavily insulated workspace on a skid mounted trailer unit that we can pull around, and it's air conditioned in here because we work on very hot and cold environments, so we have climate control in these systems. Okay, I already talked about this. This schematic up here is kind of useful because the one in the upper right hand corner, it just shows that we have these laser diodes that pump certain wavelengths of light out into the fiber, and it basically sends that downhole. And it probes the wellbore with transmitted light. As it's transmitting forward, some of the light's coming back at us, kind of like radar or sonar. It's the same thing with sound, right? You put a pulse out there while it's traveling forward, some of that sound's bouncing back to you. You try to make sense of that sound. So this is like optical sonar. So when the sound comes back, even though you've launched it down this cable, as the light travels forward, at the same time you have light traveling backwards, you go through this circulator and you bring it into these receiver plates, and then you go through an ADD converter, and then you do a data processor. And then so it has to travel all the way down to the end of the fiber. And then once that backscatter energy comes up, then you can launch your next pulse. So there's really fine timing type of things going on inside of these big interrogator units. So there's a lot of sophisticated optical electronics inside of these IUs, these interrogator units. Okay, so how does it work then? I mean, so I talked about some of the setup. How does this RFS DSS or strain measurement thing actually work? Well, we use a principle or strain detection technique called Rayleigh frequency shift distributed strain sensing. And the best way for me to describe this is if you have a segment of fiber, every 20 centimeters of that fiber optic, of that glass, has a certain distribution, a natural distribution of density heterogeneities inside that piece of glass. They're not engineered. They're just, when you make the glass fiber, there's natural kind of density heterogeneities in it. Well, though, if you pump light down this piece of glass, as the light backscatters, you get a certain frequency fingerprint. So this is frequency versus amplitude. So this 20 centimeters has a unique fingerprint, just like each one of you has a unique fingerprint. So fingerprint for 10,000 feet every 8 inches. If you change the shape of that fiber through strain, if you squeeze it or stretch it, or you heat up the fiber, the temperature changes and it thermally expands or contracts, or if there's vibrations that are passing through there like sound or acoustics, then the frequency fingerprint won't change, but its position along this frequency amplitude space will shift. We can measure this shift, and that shift is related to the strain change. So this is the fundamental principle behind Rayleigh frequency shift distributed strain sensing, is this aspect or this frequency shift. And in general, this tool has the ability to measure less than 0.5 microstrain units of change over a certain interval of time. And it also has a sensitivity on the order of 0.1 degree Celsius. So just to put that in perspective, if you're not familiar with what a strain or a microstrain unit, also known as an epsilon, micro epsilon unit, one micro epsilon is 10 times 10 to the minus 1 times 10 to the minus 6 strain units. What is a strain unit? It's basically dimensionless, because if you think about it in terms of physical length, it's like 1 times 10 to the minus 6 millimeters of change over a 1 millimeter length of fiber. So this thing has very high sensitivity to strain changes. Okay, so this is just an example. This is a very busy slide, but let me just start up here in this upper right-hand corner. The change in the Rayleigh frequency, this is the delta mu r, basically the Rayleigh frequency shift is related to a coefficient times the change in the strain plus a coefficient times the change in the temperature. So this is one kind of like, this is not a panacea, right? I mean, this is one hitch about Rayleigh frequency shift distributed strain sensing. If you have both delta T and delta mechanical strain happening simultaneously on a segment of fiber, you can't tell with this information, you can't deconvolve it or separate the two things that are driving it. But under many situations, we don't expect a lot of mechanical strain to be happening. It's driven primarily by thermal strain, or vice versa. There may not, in certain situations, there's not a lot of temperature change going on, but we know there's a lot of mechanical change going on or strain going on, like in a frac. So just to show a picture here, very simple picture here right below, is that this blue fingerprint, this is frequency versus amplitude here. The blue is the fingerprint at a certain time. I'm going to call it time 0. The red is the fingerprint on that same piece of fiber n seconds later, but you see how it doesn't match, right? It's been shifted. So you could just use easy, simple mathematical cross correlation. Here, this is a cross correlogram to figure out what that frequency shift is by virtue of where the cross correlation peak is. So here you can see that the cross correlation peak is at about like minus, 38 gigahertz. We're measuring in gigahertz here. So this peak tells you can be related. That peak, that shift right there is that value. So when you apply that shift or that lag to the change trace relative to the references, you see how they line up, right? There's very little error there. So that means you got a good match. And that lag is what tells you what the overall strain change has been. So that's a very important principle to understand. And, that measurement is made, let's say you got a 10,000-foot well. That measurement is made from the wellhead to the end of the fiber every 8 inches along the fiber. So and then you're basically collecting a profile along the entire well. You take a baseline profile, that's your reference. And then you make a new profile. It maybe takes 30 seconds to make a new profile. And then you get another one 30 seconds later. So that's your delta T between your profiles. So it's like taking a full log along the entire well every 30 seconds. And the fundamental measurement then is to measure the change in the strain from the baseline reference to that new profile. However, you can set the reference profile wherever you want. It's an arbitrary. If normally we just kind of set it when we start recording under static conditions, and we just kind of watch that over time, how things are evolving And that's the cumulative strain change through time. But we could come along, we could say, okay, I want my new reference point to be here because I'm in a new setting and I want to start doing the strain change from that point forward. So it's pretty versatile in that manner. DAS works a little bit differently. So what I was talking about before is called Rayleigh frequency shift distributed strain sensing. DAS is a distributed acoustic sensing technique, and it is responding to molecular scale vibrations along the fiber. So rather than having a spatial resolution on the order of about 20 centimeters, like this RFS DSS, the DAS typically has a spatial resolution of about 1 meter to 2 meters. So, you know, it's much coarser relative to what it can measure in spatial coordinates. The benefit, though, is that DAS is making an entire well profile about every 1/10,000th of a second or 1/5000th of a second. I mean, that's 5,000 hertz, 10,000 hertz. That's the native frequency sampling of DAS. The native, so it's kind of, and you can parse that data. You're getting from near DC out to 10,000 hertz. And you can slice and dice that data however you want in acoustic space, which is very valuable. The RFS DSS measurement is a slow strain measurement. So, right, I mean, if you're only making a measurement every 30 seconds or so, you're really kind of watching the strain evolve, this what we call the slow strain, which is usually good enough when you're measuring frac. I mean, when rock is breaking, you know, it's usually you're looking at, when you get into flow dynamics and fluid flow and well bores, RFS DSS is too slow, right? I mean, if flow dynamics and all that is being driven by thermal changes up a pipe, then a lot can happen in 30 seconds. But if you're using DAS, it's recording so fast, like, you know, 1/10,000th of a second. You can see a lot of fluid dynamics in pipes and out of orifices, you know, perforation, flow, acoustic noise coming through perforations and so forth. So DAS has its purposes, and no special equipment is used downhole. I mean, it's just a single mode fiber, just like RFS DSS. So that's one of the benefits of this cable is it's got two single mode fibers for us to use. So we can be measuring slow strain with RFS DSS and DAS simultaneously during any phase of the project. So I'm not going to get into all the physics of this, but DAS is a well-known technology. The other companies that you work for, or that work for you, that work for you, they have DAS technology and they have distributed temperature sensing, but they don't have this RFS DSS technology. This is a proprietary, patented Neubrex technology. Okay, so who cares about all this stuff we've been talking about? I mean, who cares? I mean, why does it even matter? Well, this is why it matters, because this is what you can measure on Forge with this type of data. So I got a short series of examples here. I'm going to go into more detail later on, but this is the RFS DSS strain rate measurement under fluid circulating conditions. And if you're not real familiar with looking at this kind of data, let me describe it real quick. This is called a waterfall plot, if you're not familiar with it. So a waterfall plot has two axes. It has your depth axis down the wellbore from surface. Here I'm just showing from 4,000 feet down to 10,000 foot. This is MD, RKB. That means measure depth relative to KB. And the end of the fiber is right here. So whenever we use fiber optics, we're careful to register our fiber measurements against wellbore measurements. So everything is always labeled as MD, measure depth, feet, RKB. So that's the vertical axis. The x-axis here is time. So depth versus time. And then what's being represented here in color are the measurements themselves. So I talked about all those profiles that are made down the wellbore every 30 seconds or so. You don't see the traces here, but these traces are represented by color. So this is a waterfall plot, and I'll get into this. I'll get into this later on how to interpret this, but what you can associate, what we like to do, what really brings value is when you associate or correlate the downhole fiber optic data with other measurements. So for instance, here we lock pressure and temperature gauge data that's collected down the hole on a Baker Hughes PT gauge. We lock it by time. So both of these things, the downhole gauge and even surface equipment, it's all recording on GPS time, right? There's a clock. And that's what ties our measurements to every other measurement that's made on a well pad. So in this particular case, this is a circulating well bore, and I'm going to show you here that when they were, this is the B well. All the measurements that we make on the Forge project are on the B well, right? They're not on the A well because we don't have fiber in the A well. But if you look at a short circulation test, this is prior to, well, I probably shouldn't get into all this, but basically, when you see all this green, that means there's no change in the thermally driven strain downhole from 4,000 foot to 10,000 foot. But when they start pumping on the 16A well and we start to see pressure occurring on the gauge on the 16B well, you see this light up from 4,000 foot down. It means that there's pressure, or there's a thermal change that's occurring in the B well. And so you can interpret these things to know where temperatures are changing in time and in depth. You can see whether or not fluids are moving down the well, down the 16B well, or they're moving up the well by virtue of these types of things. And this proves that there's an actual physical relationship between pressure and thermally driven strain. Because you see this little change, or this change in the delta temperature over delta T. That's what all this red stuff is in the bottom of the 16B well. This is hot fluid that's being moved from the 16A well to the 16B well. And these are the original fracs that were put into the 16A well in 2022, pumped in 2023, but you're moving hot fluid across the reservoir into the B well. You can see that in the temperature-driven strain anomalies here, this hard red stuff. And you can also see it in the pressure coming up on that downhole gauge at 7,000 feet.
So just to clarify on that, we've got it labeled fast.
Yeah.
We're just referencing. So the whole length of the leg is sensing this thermal impulse related.
But that's because fluid is moving up the 16B.
Oh, this is the fluid moving. It's actually
Yeah.
Well.
It enters. It's actually entering. It's entering way down. There's actually entry points below the fiber here, right? You got open hole on 16B, and then you've got a little bit of cased hole below the end of the fiber. So there's fluid that's moving up the 16B well, and it's entering back here, but then it rapidly moves up hole, so it heats up the entire well.
Understood.
Yeah.
Thank you.
Only temperature 72.
Well, it might be the scale too. You zoom into this stuff, you can see move out. You can see slopes and things like that. I've got some good examples of slopes on some later plots.
Turkey sandwich or something for you.
Yeah, sure. Yeah. Yeah, and a Corona. The other thing I'm going to point out is the sensitivity of the fiber optics. So what's really, we know the gauge is very sensitive, right? You see these little blips in the pressure gauge data downhole. All these little pressure increases and little blips, they're reflected in the fiber optic data, because the gauge sits right here on this horizontal line at 7056. So there's a correlation between the pressure coming up on that gauge and temperature coming up also. So I'm not going to go into the interpretation of that. It just shows that there's often a very good correlation between downhole pressure changes and fiber optic changes. Okay, just another example, just overview. This was the RFS DSS strain rate data from fracture-driven interactions during the 16A frac at the 16B. So that's a long title, but that's what it is, right? So we're trying to measure strain rate, right? On the B well, while they're pumping on the A well, fractures, hydraulic fractures are being created from A, moving through the reservoir towards B, and they intersect the B well. They probably keep going, right? The B well is just a plane in
Right.
space. So the fractures are moving from A up to B, stage by stage, because this is a stage-based frac process. And each one of these features that you see in this data are cross-well fracture-driven interactions. And these are classic fracture-driven interactions that we can see. And you can see how, right, this is the B well. So we're only in the bottom of the B well, really. During all the work that's been done so far, we haven't even got up to the heel of the well. So we're showing evidence that the reservoir has been stimulated from A to B. So this is a RFS DSS strain change rate waterfall plot. That's what we call it. You can see that this isn't no data. This is just no strain data, right? There's no strain change occurring prior to us pumping. It's nice and quiet. It's not until we start working on the A well, like when they do a pressure test on the A well, you can see that there's an effect. Even when they pressure up the A well, there's an effect over at the B well. So these things are connected. And then we start seeing all the cross-well frac hits. What's tied in time here are the pressure pumping curves from 16A. So this is standard oil field stuff where you're always trying to relate rate, pressure, proppant density to what you see in the far field. And it's all tied together by GPS time.
Right-hand side of your plots. This is true for the one you showed before.
Yep, after the A well was stimulated, the B well was opened up. So you start to get all this fluid moving up. You see all this slugging here. You see these slugs. That's fluid slugging up the hole after you frac stimulated A. And I assume that since the B isn't open yet, except at the bottom, that's fluid moving up the B well. That's fluid moving up the B well. This
It's the contours, like there's overlaying red and off each other, right?
Yeah, it's complicated why that's occurring out there. I don't know. I can tell you that all this noise out here is because changes are occurring so fast that it exceeds the ability of RFS DSS to properly work. Yeah. If you had DAS data during that time, you'd probably see a lot more coherency in the patterns. Okay, so that's a strain waterfall plot. This is the same strain waterfall plot, just viewed in a different way. I kind of wanted to show this because there's a lot you can do with integrating data sets. So this is the fracture-driven interaction strain rate data here. This is what we just looked at, just different kind of color bar. To your question, if you look over here with this color bar, you see after the last stage of the 16A frac, you see how you've got that move out? That's the hot moving up from the bottom. It's moving up hole. So it's not moving in from here because none of this part of the well, the well isn't really perforated yet. The B well isn't perforated yet or opened. So everything's moving up out of that open hole into the B well. You can time tie this to your treating pressure and your slurry rate on the 16A well like normal. And what we did here was we integrated the rate curve to give you the cum volume, and we can start to relate certain features that we see in the data in the crosswell strain pumped on the A well. So this is a common thing they do in oil and gas, where they want to know what the volume to first arrival or first response is. So this helps them do some optimization work in terms of what they're pumping and volumes and so forth. So you can see there's a lot of variability too in the total volume pumped, the slurry volumes on these different stages. I mean, stages 3R, 4, and 5 had pretty small volumes compared to these later stages. Stage 6 was, I think this is stage 6 right here. This was kind of a bust of a stage. They couldn't get this job to pump properly, and there's hardly any volume pumped. Stage 7, very interesting stage. It looks very normal, not only in terms of its pumping pressure curves, but also in terms of its cum volume. So we'll get into that kind of detail later. But so there's a lot you can do with engineering data from the surface tied to downhole data.
And just for clarification,
Yeah.
are you going back to that last slide?
Yeah.
Will you be coming back to the negative versus positive strain?
Yes.
Okay.
Yeah, I will. Yeah. Okay, so you can take this kind of data, and we know how to kind of basically look at the overall crosswell fracture strain that's been produced by the hydraulic fractures at the 16B well and look at those in one fell swoop. So rather than looking at each individual stage, we can generate a depth series that shows all the strain that's occurred. So this is all the strain that's occurred on the 16B well from the bottom here to up around 8,700 feet, which is the kind of the last active crosswell frac hit that we saw. So we can look at this stuff. These curves have 20 centimeter resolution down the fiber. And so all these little peaks tell us where, like, very discrete fractures intersected that B well. And then we can catalog those things. We can give each one of those a catalog number. And I mean, it's arbitrary, right? It's interpretation on what you pick. But this is what we did in the field. We picked all these peaks, which are cataloged here, and we used these picks in the field to say, okay, here's the catalog number, here's their exact depth. Now what we want to do is we only have 20 guns to perforate the 16B well, because we couldn't use wireline perforation. We had to use tubing conveyed perfing guns because it was so hot, because all that fluid was traveling up the B well. So we had to high grade 20 of all of these picks, which is done here. So we picked 20, and then we segmented those into stages. This was done by myself and Kevin England and John and Leroy, and we kind of picked 20 individual points out of all of these picks to say that's what we're going to target when we frac stimulate the 16B well. So this is a product of the crosswell strain monitoring.
So those are the individual clusters
Yes,
within each stage.
correct. Right. And then you can see that we've kind of so these picks are, this what we're going to do on 16B. Stage 1, clusters 1, 2, 3, and 4. Stage 2, 1, 2, 3, 4, 5. Stage 3, 1, 2, 3, stage, and so on and so forth. So if you total up these total number of arrows, there's going to be 20 of them. Okay?
So prior to perforating B.
Correct. We had to pick our targets. Yeah. So this is target picking right here. Done in the field. So here's the 16B plan. So here's the pumping schedule here in terms of, fluid type, fluid volumes, rates, and then proppant type of things. How many clusters per stage? And then this table was derived from that work right there. So these are our targets for each stage. It gives the little the depth interval of each cluster and the gun that's associated with it and where we're going to set the frac plug on each stage. So this table was made to give to the the perforation, the pumping crew, basically. So then once you start pumping those stages on 16B, you've got fiber in the hole, you're perforating. Hopefully you don't perf through your fiber, right? You're shooting guns off, blowing holes into this casing string. You have to orient your gun so you don't blow through your fiber. But if you don't, which we didn't, then you can turn the DAS unit on. And the DAS is recording very fast, and it can measure acoustic noise. So if you're pumping, once you start to, you set a plug, pull out a hole, run in hole, perforate, pull out a hole, and then you pump your hydraulic fracture job. When you're pumping your hydraulic fracture job, that plug tends to rattle a lot. It makes acoustic energy, and all the fluid leaving those orifices, those clusters, make noise. So you can hear that noise. And I have a presentation later on this, but you can see the acoustic energy in these lines here. Again, this is depth versus time. So when you have one of these linear features like this, where it's that's a line of noise. That's the perforation cluster noise at that perforation. And the amount of noise, a simplistic kind of idea is that when you have one cluster that has nice consistent noise over the entire pumping period versus another cluster that's weaker or only has acoustic noise energy over a certain limited amount of time, the one that's better took more fluid. It took more slurry, because that's called, that helps you get to uniformity indexes and cluster efficiency and things like that. Because rarely do you see a stage with multiple clusters in it all take the same amount of fluid, volume of fluid, or percentage of the total volume pumped. There's variability. Sometimes it's heel dominated, like the heel most cluster takes most of the fluid. Sometimes it's toe dominated. Sometimes looks random. You don't know why. So we've done that when we pumped the 16B, all 4 stages. We got this kind of data, and I'll show you that later on. So
if we have, say, stress shadows over the pumping period, we might see some fracs grow early and then some fracs grow late.
Yeah, that's right. Yeah, because that's right. If you see stress shadowing, sometimes you'll see a fracture that's dominant. The other fractures are trying to grow, and then they just die. And to me, that's because a dominant frac. You got to realize this is near wellbore.
Yeah.
Right. This is real. This stuff is near wellbore. What we did 16A to B is far field. This is near wellbore.
How near well? What's the line? Let's go.
It's
Here, 2 meters, 10 meters?
Well, no, I mean, you're making the measurement right in the cement sheath.
Yes, so that's as far as it goes.
Well, I mean, you could tell me, I mean, you're pumping fluid through an orifice into a hydraulic fracture that goes out into the formation. So if you have continual fluid or slurry flow through that orifice, through that one cluster that continues to take fluid the entire time and makes noise.
So just use the pump volume to kind of get an estimate of how far it's extended.
Right. But if another orifice set, another cluster dies after a certain amount of time, it's probably not taking fluid anymore. Right. And it probably means that fracture died out into the far field. The alternative, though, is that you get a lot of erosion on these perforation holes. And Mark, McClure just wrote a little blog article on cluster erosion and what its effect is. A very interesting little blog post, because the change in the shape of that orifice will change the noise profile also. It's got to. I mean, a tuba sounds different than a flute. Why? Because the orifice diameters are different, right?
Sure, yeah.
That's the main principle of music. So, I mean, we're never quite sure if the noise is changing because of the orifice change dynamics, erosion, or if it has to do with intake, or how much slurry is that orifice imbibing, or does it bridge off? I mean, we always want to say it bridges off, but I think that the other factor is important too, erosion. So this is just another example of use. This is an example of a product that comes out of that use. So on this particular stage 2 of 16B, we looked at the 32 to 128 based DAS solution, and we know how to use that DAS information to calculate the amount of fluid that each cluster took on a relative basis. So that's an injection allocation solution right there, by perforation cluster in a stage. So I have a presentation on that. I can show you that later. And that's important, right? That's important for completions designs, really. I mean, that's what completion engineers do. Completion engineers are trying to optimize that profile. They don't want to take the time to basically blast 5 clusters into a wellbore and one of them isn't taking fluid, right? That's inefficient. You want to get high efficiency, high uniformity across all clusters during a pump job. Okay, so this is just, I'm not going to go into this too much, except to say that we can take all of this data and we can calculate logs and then correlate these logs that we generate from the raw data and compare them. So for instance, this is a frac log. So if we go back to that depth series log that I showed back here, right? So this is basically a log. This is depth versus value. It's just like a log. So we have a log, a frac log down the wellbore, depth versus a value derived from this raw fiber data. And then we can also generate a fracture, a post-frac circulation log. So when we start flowing fluids from A to B, we get this plot over here, which is the fluid coming into the B well. And we can pull some windows from this data. We can do some integration work, numerical integration. We can create a log of where the fluid. It's basically a fiber PLT. And it's not mechanical PLT with a propeller, it's thermal PLT. In this case, the RFS DSS data is being driven by thermal changes. So it's like a thermal PLT log, but it's a good indicator where the fluid is entering the 16B well.
So on this one, just really simplistically, there's the blue, the yellow, and then the red.
Right.
So most simplistically, what is that represent?
Yeah, and simplistically in this particular color scheme here, the red is cooling. You see these things, these slugs that are kind of coming here that kind of go down like this. This is cool fluid that's getting into the B well, and instead of traveling up the B well, it's actually running down the B well. The blue, this color bar is reversed to what I normally use. The blue is warm fluid, either hitting the well, right initially, or it's slugging up the well bore. So these blue are hot fluids in the well bore. This red, yellow thing here, this is a cold slug moving up the well bore. So future presentations that I'll show you, I flipped to a more normal color bar where, blue is cold and red is hot.
You're gonna come back to that slide?
Yes. Yeah. The key thing I'm trying to say here is that, these types of plots are pretty complicated, hard to digest. Engineers, geoscientists, we're used to looking at logs. So we have ways to kind of extract information from these types of plots and make log plots that tell us where where fracture-driven interactions occur, where most of the fluid is entering well bores, and so on and so forth.
Those are over short time, incredibly short time scales that those are happening, aren't they? What's the time scale at the bottom?
I mean, these are hours. So that's 2, 4. I mean, they're not that short. I mean, these are in hours.
Geologically, that's pretty short.
Yeah, we don't work in geologic time. We work in engineering time. I mean, these are processes, right? You're pumping in hours, not days and stuff. So, and some of these things happen in a couple minutes.
That's fast.
Yeah,
Or
faster. Some things happen in milliseconds. That's why we record DAS at, you know, a 100th of a millisecond. Speaking of which, this is DAS data. This is DAS microseismic data. So that fiber down that 16B well is being used as a huge geophone antenna. And as I don't know exactly, I think we were pumping, but there was microseismicity that was occurring. So this is far field data. So here's the well with the fiber in it. There's like a microseismic source event that occurs somewhere out in the far field here. And when it slips, it generates a P wave and a shear wave that travels towards the B well. And you can see the move out. You can see the P wave signals and the shear wave signals. And actually, I mean, this data is rich, reflections and everything else in this data. But this P wave move out curve in red and this blue move out curve is the shear wave. This information can be used to locate where that source is, where that microseismic source is out in the far field. So that's what microseismic is about. So if you do that repeatedly on thousands of these things that are called triggers from the data, you can locate all of the microseismicity that's occurring out in the far field away from the wells.
They tell how far away it is from your cable. You can't get direction.
Correct. In this case, yes, but they got.
Can you describe what you mean by 3C? That usually means 3 components, but you don't have 3 components.
They did in the vertical wells.
Oh, okay, so you're combining it, yeah.
Yeah.
This is not.
Correct. That's right. This basically gives you maybe the depth and a distance.
Sure.
That's about it. You're absolutely right. And then they combine it with the downhole geophone data that was also being recorded. And they were doing this real time in the field and mapping the microseismicity. Yeah. So yeah, that is a limitation. Although I always have to wonder because the wellbore trajectory here, you do have a vertical section that's fibered up, right? So if we had been recording in that and the slant section, could we didn't here, but could we have used the vertical section to kind of hone in more, triangulate on the location? But it's not 3C. Absolutely. It's not, you can't run a hodogram or anything like that. But the benefit is if you got 9 geophones strung out over thousands of feet, your spatial sampling is on the order of 100, I don't know, 50. I don't know what their spatial sampling is. The spatial sampling of a geophone array is much less dense than a fiber array, which has got 1 meter spatial sampling. So it's, there's pros and cons, pluses and minuses. Just the color version of that. And that's the end, kind of the introduction there. So I'm Dana Jurick. My co-author here is Arthur Guzik, and the man that did a lot of the field work out here is Wayne Fishback. He's our chief of operations.
Great.
Okay. Do we want to keep going here, Joe?
Can
Or
we take a 15-minute break?
yeah.
There's one question in the chat, Dana. I don't, if you want to take the break first, but just so you know, there's a question in the chat.
How do I get to the chat?
I can just read it to you so you don't have to go out of full screen. It's from Scott. What about perforation erosion? Wouldn't that change the acoustic response near the wellbore?
I talked about.
Okay, sorry.
That's all right. But the answer is yes. Yes, that is a definite issue that can muddy the waters, no doubt. That can muddy the waters of trying to use the acoustic data as a quantitative measure of injection allocation, no doubt.
Well, that was great for me.
Good,
Thank you.
Yeah, that was excellent.
good.
So. Come back in 15 minutes.
I don't think we're muted. I don't know.
I'll mute
Sean,
everybody.
Yeah.
Hey, Dana, you're on the presenter screen, so you have to switch over. Okay, looks good. Hey, everybody, we'll get started here in a minute. Hey, Dana, you're back on the presenter screen. Okay, looks good. Whenever you're ready, go ahead. Yeah, yeah. Okay, Dana, I think we got it now. Sorry, everybody. If you want to get started, we can see the full slide.
Mute. Okay, can you hear me, Sean?
Yes, I can hear you.
Okay. All right, very good. So what I wanted to do, what I'm going to do for the next couple hours really is to step through different, what we call evolutions of diagnostic fiber optic monitoring that were done on this project. And I kind of talked about that in the introduction. We kind of have this pyramid of different measurements that were made from cement operations, installation, cementing, circulation test, hydraulic fracturing on 16B-A and then 16B in the circulation test, and then finally monitoring this extended 30-day circulation test. So what we're going to start with here as a foundational element is the cementing operations.
Have that slide again? Is
Um,
that easy? We've got a whole bunch of new.
yeah, let me just, I have it on the other presentation.
Gonna get complicated, Joe.
Yeah, yeah.
Yeah, then don't.
So anyways, there's just, let me just say it with words then. I mean, the fiber optics that are installed in this 16B, what we call the monitor well initially, it starts out with monitoring the cementing operation. Once the casing string with the fiber was cemented in place and cured, then there was a circulation test that was run from the original hydraulic fractures done at the toe of 16A across the reservoir into 16B. And we measured that 16B, initial circulation test in July of 2023. So that was what this subsection is about. So again, that acquisition date was July 2023, and this work was done by Dana Jurick, myself, Dr. Arthur Guzik, chief and software engineer and data processing services, and really our entire team from the field and from data processing and business support. Okay, so evolution 0 is what we called the cementing operations. And I'm going to move this out of the way here. This is just from a report. A lot of the pictures that I've taken here for these presentations are reports that have been delivered to Forge and are in the process of being uploaded to the GDR for reference. So the main objective of cement monitoring with fiber is to monitor the details of temperature, strain, and acoustic emissions during the cementing operations. So Neubrex would use the available fiber optics provided by the operator to make distributed fiber optic sensing measurements during that. So DFOS is the acronym for distributed fiber optic sensing, if you hear that term, DFOS. Some people use the term DAS. DAS isn't really an appropriate term to use for all fiber because there are many different types of fiber optic measurements you can make on fiber, not just distributed acoustic sensing. And so, for instance, on this particular job, we used Rayleigh frequency shift distributed strain sensing, also often referred to as RFS DSS, using a specific Neubrex instrument type. We also used Raman DTS temperature sensing. We used Brilliant gain spectral sensing, which is an absolute total strain measurement. And we use DAS, distributed acoustic sensing. Now, what were the sensing goals? Was to track the cement pumping, as the cement runs downhole inside a pipe and then up the annulus and cement's in place, and what does the curing of that cement look like as the cement sets? And do we see any flashing or unequal distribution of cement? Well, Cement is known to be a key feature of wellbore architecture, especially when you're doing hydraulic fracturing and flow and things like that. I mean, it's an essential element of the performance of that well for the life of that well. So we thought it would be good to kind of get a handle on how did the cement operation go, because there's so much you cannot know by just watching pressure pumping on the surface. You're watching nothing downhole. Okay, so just interrogator unit connections, just a schematic. Here's the well bore, 16B. We're using the single mode fiber 2 because there's 2 single mode fibers. We were on single mode fiber 2 here and multi-mode fiber 1. We're using the Brilliant, the Rayleigh, and the DTS instrument. And we actually had the DAS running on part of this work also. Something about optical loss. You can, on single mode fiber 2, you can measure the health and the transmission and the backscatter quality of the optical signal that you're pushing down that fiber. This is actually the backscattered optical loss. So this just means that I push a pulse down. I know what that pulse is. It's coming back at me, and I can figure out how that transmission loss occurs as a function of distance down the wellbore. So this wellbore is from surface to about 10,000 feet total depth. The fiber's 10,000 feet long. The well itself is a little bit longer because we didn't go to TD. And this is in decibels here. So that's a measure of energy. It's a logarithmic scale. And this fiber was in very good shape. The loss on this fiber was very small, on the order of less than 1 decibel over 10,000 feet. So very good installation job. This is the only way to really tell that. This is diagnostics should always be done on any fiber that you're going to work with. Another way to kind of pre-assess or assess the fiber character is using the Rayleigh tool, the Rayleigh frequency shift tool effectively. Another way to kind of look at the initial characteristics in a wellbore, and I think this was done pre-cement, right? So the fiber's on pipe prior to cement, and you measure the total absolute strain every 20 centimeters on the fiber. So the fiber, it's in the earth. I mean, at this point, right? I mean, there's just a little bit of an annulus. So when you measure the total absolute strain value, the total absolute value of strain as a function of depth down the wellbore, before you start doing anything and flowing and cementing and everything, it's effectively the best geothermal gradient tool you can get. It's measuring the total absolute strain initially on the fiber is driven by the thermal characteristics. So you can see in this case that you have a normal geothermal gradient coming down the vertical well, and then you kind of, it flattens out as you come into the slant because you're not, your gradient, your deviation isn't vertical anymore. You're gaining less vertical depth with distance, so it flattens out. So this is just another indication that the fiber is in great shape initially from top to bottom, and we're getting a very good, probably the best geothermal gradient, because you can convert these absolute strain values to a temperature. This is just a picture of the gauge. So there's a gauge here at 56 feet measure depth in this 16B well. And July 13th, it was working fine. I don't know about the pressure, but the temperature part looked real good compared to our fiber measurements. We don't have a direct pressure measurement from the fiber. So I don't have a way to calibrate or check any pressure measurements on that gauge readout.
This is this year or last?
That was last year. That's 2023 right there. Okay, so I went to the pre-cement pump job. This was the job that was posted by the company or by the contractor who pumped that job. And This is Leroy's console of that pumping. So we get information on pressure and rates and times and volumes that we kind of captured in our observer logs. This is important that we capture information about what was going to be done, what was done, and what did they actually do, and at what time they did things. Because like I said before, all of our fiber data is measured in time, GPS time stamped. So if we have other stuff that's being done and recorded in time, that's how we correlate everything in time.
So the information you're uploading to GDR, is it obvious that it's UTC?
Yeah, we put a header in there that it's all UTC. And you know why it was UTC? I mean, that
Yeah,
we were directed,
discuss
yeah. Okay, so
Somebody under the bus.
yeah, no, yeah, I mean, yes, we will ensure that everything says, hey, this is UTC, which is local time. You know, it's UTC -6 is local time. So, yeah, it's something we have to deal with. Okay, so this is really this is just the initial work that was done after the iron was hooked up for the cement pumping job. You can see this is strain data. These two plots are strain. These are temperature plots prior to any pumping or pressure testing. The waterfall plot of depth versus time. All this green shows is there's no strain change really occurring. Everything's quiet. Once you start putting pressure on the well, you start to see signatures on that fiber down the well before they even pump cement. I mean, you're putting pressure on the well. So this indicates that the system is sensitive.
Wait,
Go ahead, Joe.
no. So on the temperature, when is this temperature measured?
This is
Is it pre-pump?
pre-pump, and then while they just started to pressure up on the iron. This is field data.
Yeah,
This is not calibrated final DTS data here. Okay, so when we do our final processing, we calibrate to the gauge and do some correction work with our brilliant geothermal gradient work. So whenever I say that this is like a field monitor, be careful about taking especially the temperatures verbatim because they haven't been fully processed yet.
that's in the process.
That's done. It's all done now. It's just
Okay.
that these pictures I'm showing, the ones I grabbed here are field monitors.
But this is basically just showing a linear variation in temperature with depth.
Yes,
There's nothing
Right.
odd here.
right. Now, it probably looks a lot like this, where when you get into the slant, the gradient flattens out, which is what it should do. And this axis here, Joe, is not temperature, it's in raw gigahertz, so it's still in optical coordinates or units. Okay, so they did some pressure testing on their pump gear, then they pumped a spacer, and you can kind of see once they pump that spacer, you get a signature on the RFS DSS strain rate data. And as that, this is an RFS DSS strain rate raw field plot. And what it shows, these vertical stripes are basically, they pressure test the well, and then they start to actually pump cement. And because there's spacer in that wellbore, right? I mean, guys, correct me if I'm wrong, but there's fluid in that 16B wellbore ahead of the cement. And when they start plunging on that wellbore, when they first start pushing cement down, immediately, if you look down here at the bottom of the cable, there's a thermal slug that's moving up the wellbore. So there's heat down there that's now you're pushing down, there's heat moving up the annulus now. And this inclined line here is the cement front moving down the wellbore towards the bottom of the well. And there's a whole, as you do that, is that that cement is moving down here at the bottom where this V is. That's the cement that's hit bottom. And then it's moving up the wellbore now. And as that's occurring, you're pushing these thermal slugs, all these vertical lines that are red here. These are thermal slugs that are being pushed up the annulus ahead of the cement. So, just dynamic observations here, really off the field.
So here again, negative strain and
So a negative strain would indicate, in this case, some cooling. Positive strain, red here. And I know this can get confusing on a field plot, but you see this negative number over here, red? A negative frequency shift in RFS DSS base is a positive strain change. So remember this morning we were looking at the lags, we were looking at the fingerprints. So if the new trace has to move backwards, if that's a negative frequency shift, that equates to a positive strain change.
Positive is compressive.
Yes,
Okay.
yes.
Okay.
No. Positive is extensional.
Okay.
Negative is
Okay.
you're shrinking it.
Okay.
So you got cool fluid moving down the wellbore, it tends to create a shrinking effect. As you have heat slugs moving up, they're expanding.
See, most geomechanics people use compression positive. So there's always this level of confusion.
Yeah. Well, I think about it in length coordinates.
It's the same.
Yeah.
If the length is being smaller, it's compressive. Oh,
To me, that makes more sense. If the length is getting shorter, it's a negative change. Here, shorter, change is negative. Because we're thinking of change. Okay, yeah.
doesn't matter.
We can use whatever color bar you want.
No,
Yeah.
it doesn't matter.
Yeah.
And if it's
Yeah.
consistent within the fiber optics community, then we
Yeah.
don't want to change.
So as that pump job went on, I'll just say that, we continued the cementing, and then the pumping operator had a problem with one of their trucks and they had to shut down for a little while. And so there's a change in the slope of on the strain rate. You can see it, how it just flattens out because they weren't pumping here. Then they start pumping again. You get this big slug move up the wellbore. And then at this depth, I don't know if that's because it's flashing or what it is, but you get these heat slugs. You remember this? We had these anomalous heat slugs that occurred after they started to repump. And then the cement slug, the cement just moved up the wellbore normally. The only thing that's abnormal in this whole image here are these clear thermal, positive strain changes that are occurring up above 3,000 feet in that wellbore. I don't know what they mean, but they're anomalous.
There was no, and we should get Kevin England to comment on this, but there was no cement above about 2,800, 3,000 feet.
Mhm.
Kevin, you remember?
Yeah, John, that's probably right. I think there was minimal cement, somewhere in the mid 2000s, to surface. There was some water, and then, at the top, it was pretty much completely evacuated.
Yeah. So maybe that's the heat hitting the water and steaming off.
I don't remember there was any flashing or steam during the circulation. We should have been circulating it at much less than, where any water would flash, but definitely, there, with the shutdown, there were things that were gelling up and some real anomalies in the displacement after we started pumping again, for sure.
Well, these depths on a field plot don't have the surface fiber taken out of these plots right here. So that's right at about 2,500, 2,600 feet.
Yeah.
That's occurring. Okay, so here then the cement. I remember seeing some thing that looked like cement coming, out of the pipe into the pit. So something hitting the surface here. You can see this.
It only looked like cement.
Okay. I don't know what it was, but something, this feature makes it to surface on the fiber because the fiber goes all the way into the wellhead. So again, and these things are rising through time through that column. So there's just an overview. So this is the cementing period all through here. So we monitor that with the strain fiber optics, the RFS, DSS. This is this cumulative strain change here in the center. And then this is the strain change rate. I mean, I covered this morning a little bit. The primary fundamental measurement is the RFS DSS strain change. That means that we take an initial fingerprint every 20 centimeters down the fiber, and then we compare the next fingerprint 30 seconds later to it, and we say, what is the change? What's the frequency change on every one of those 20 centimeters? And then we equate that to a strain change. So this is basically the cumulative strain change that's occurring. If you differentiate across time every single trace, that's how you get the strain rate data, right? So this is more of an instantaneous strain change. This is cumulative strain change. So once you're done with cementing, then you're done cementing right here along this right-hand line of this box, and you start to cure. So you can then look at the curing process after cement is done. And, initially it's cool and then it slowly warms back, right? So it all looks pretty normal. All I would say is that deep in the section, where you had the initial crosswell flow in 2023, or in 2022, you generated some hydraulic fractures from A to B.
Correct.
And in that zone, it stays hot. It warms back faster and warmer than everything else above it, right? That we haven't stimulated yet. And you can kind of see this in the DTS data also, down in here. So there's the bottom of the B well is quite warm.
Before you go forward, Sean, there was a question. Does it pertain to cementing?
Yeah. So the question was, did we have full returns to surface during the cement job?
So why don't we let Kevin England comment on that? He was
Sorry.
there.
Okay, yeah, go ahead, Kevin. He commented in the chat too. So.
Yeah,
Oh,
so
okay.
yes, there was always circulation to surface. I was just typing another message that because we didn't have any way to measure the actual flow rate from the annulus to the sump, so the U-tubing effect that happens during cementing with the density differences inside and outside likely got very confusing because of all the slowdowns and mixing due to the difficulty in mixing the actual cement. So really wasn't possible to tell in hindsight if things were following along pretty closely or not with that effect. So I think Scott's probably alluding to, were there any losses to the formation in some places? And I think, yeah, the answer is that cement was definitely at some point going somewhere. And then when the job was finished, we had fluid to surface, but not good cement to surface.
Okay, any other questions related to the fiber optic measurements made during cementing and curing? Okay. Anyway, so after the cement process was completed and curing occurred for several days, there was a short crosswell circulation test done from 16A to 16B. So this little section covers what we saw there. Because we called evolution 0 the cementing phase, then we called the post-cementing monitoring evolution 1. So during evolution 1, this is the fiber optic connection scheme. This is what we just write a schematic here that shows the well bore. So there's single mode and multi-mode fibers running down the well bore, like we said before. And we run a whole series of interrogator units, including the Rayleigh frequency shift unit, the Brilliant total absolute strain measurement unit, the DTS temperature Raman-based unit, and the DAS acoustic unit. So you notice that we didn't, on this cementing process, we did not run DAS because most of the changes that we're looking for during cementing are relatively slow, right? We're not looking for acoustics per se. When we get into flow circulation, we want to have DAS. Plus, the microseismic people are interested to know whether or not any of the cross-well flow circulation created any microseismicity during that period also. Okay, so this is just a time chart. It's a common way to just demonstrate which instruments were on which fibers during which time. So there's a lot of bookkeeping involved because when you're collecting this much data, you need to keep track of this kind of stuff. Otherwise, you get a disk full of data and you don't know what went where and who did what and who was on first. Okay, so this is just some depth calibration work. The people that are involved in data processing will appreciate this part. There's depth calibrations that are done on the multi-mode fiber and the single mode fiber and the different instruments to make sure that everything lines up, you know, on the different instruments on different fibers, because everything has to be aligned in depth domain. Okay, I will say that just like any good field operator, we have engineers in the field that keep detailed notes. They're called observer logs or OB logs. These track everything that we do and everything that happens on the pad in terms of the day and the time and what the event was and any notes. Because after the dust settles, nobody remembers what happened. So we track, because we're trying to correlate all of our measurements that we collect and we get into a hard drive against time. So when we start seeing things on the data that we don't know, wonder what that is, we look back to our observer logs to figure out what was happening. For instance, on the 18th of July at 13:51 in the afternoon, then the pumping started at 12:09. So he reported this at this time, but he knows he got information that they started pumping at 2.5 barrels per minute at 12:09. So he puts his reporting time here, but then he puts, all this kind of detailed information there. So on a pump test, this is really important to know because, the pump crew's over there changing his rate at a certain time. And then we walk over there and we get that information and put it in our OB logs. Other observations are, for instance, getting returns to the pit now. So, we talked to somebody and they said, okay, around, 5:57 in the afternoon, I saw pits. I saw fluid coming across into the pit. Okay, we optical loss analysis. I'm not going to cover that. It's just like we check that on every evolution to make sure that the fiber is still in good shape, that we're not getting some kind of big change in the optical loss. PT gauge data. This is PT gauge data during that circulation test, right? So this is important information to kind of tie to our data. So pre-circulation period here, you have pressure in orange, temperature in orange, pressure in blue. And so we know that this is prior to any pumping on the 16A well. This is all 16A well, but it's what we see at 16B, right? And then they start pumping at 2.5 barrels a minute at a certain specific time that we record in our OB logs. And then very quickly, we see a rise in the temperature on 16B, right? And then it flattens out. The overall delta T during that come from the baseline to that high point there is about 12 degrees Fahrenheit. So that's on the gauge, right? Okay, that's on the gauge, and the gauge is over 3,000 feet above the bottom of that hole that's open. Right, so this is way up hole. This isn't down in the circulating zone. You guys track me there, right? It's way up hole.
Is that the heel?
It's the heel. It's at the heel of 16B. That's right, yeah. And then there's various, things they're doing with those 16A pumps. They're pumping fluid. They're just putting pressure on it and then pumping again. And you kind of see the temperatures go sinusoid a little bit over time as they do things on the A well. So we can, you know, of course, later on, you'll see that I kind of put this pressure temperature gauge data against our fiber optic data locked by time, right? That's the key locking element. Distributed temperature sensing. This uses the Raman DTS unit over this range of time from late July 15th through the July the 20th. I know where the shoe depth is. I know where the gauge is. I know where the frac hits were from the 2022 frac work. And I know when they started pumping it at 16A at 2.5 barrels per minute. So, and this is on the 16B. So this is just kind of this is a waterfall plot that's been annotated with this depth and time information that's important. So this is absolute temperature now. And I don't know, Joe. I mean, I think this is the uncalibrated DTS temperature profiles, right? So you just remember this are thousands of temperature profiles. You can see the number of profiles across that waterfall plot is 1,720 profiles, uncalibrated, but you can still see the signature down there. See that deep zone in there that gets hot? That's because you're pumping on the 16A well. Even at low rate, you start to see that heat signature. When you calibrate the DTS temperature to the gauge data so that it's all locked in or calibrated to an actual gauge, then you can still see that heat signature down there from the pumping on 16A. It's just not as dramatic. So if you go up in here on the temperature scale, you know, this temperature down here is probably in the 380 range. So there's your 350 to 400. Right. So that zone in there, just after cementing and curing and then pumping a little bit on A, you can see that heat up relative to what it looked like prior to pumping. I mean, that's the key thing here, right? Is what did it look like before you started pumping on A and to when you started pumping on A? And see it go up? I don't, it's probably pretty crappy on that screen there.
Yeah, you can see it, but that seems very rapid.
It is. I mean, I don't know what to tell you. That's what the data says. It's rapid. I mean, you know, one hypothesis there would be that there's hot fluid sitting in fractures in the reservoir, and you're just basically, when you start pumping down the 16A, you're putting a plunger behind it. So this isn't necessarily the fluid that you pumped, it's the fluid that's sitting in the reservoir that you're not pushing into the bottom of the B well and moving up the hole, right? So it's heated. It's reservoir heat. So maybe that's why it's rapid. It just takes pressure on it, like a syringe. Okay, so this is just to demonstrate these are a bunch of DTS profiles down the wellbore. And right in here, you'll just see this is a series of gauge temperatures at different times. And it just shows kind of calibrated the DTS profiles with the gauge temperatures, that we're not just, you know, the DTS fiber data is not just floating out there crazy. Another way, there's many different ways you can look at time series data and depth series data. So this is a series of depth profiles. Each one of these lines is at a different depth plane from 1,000 foot down to 9,000 feet as a function of time. So you can see that if you look at all these depth profiles from 1,000 foot down to 9,000 feet, as soon as you start to pump on that A well, the fiber senses that rise in the temperature very quickly. See it? See how it just rises and then it just kind of flattens out once they kind of flatten. And then they go through a whole series of, you know, pumping, raise the rate, and flatten, and then raise the rate. And you kind of see these temperature effects at different depths along the wellbore. All right. Gonna skip these. Now, another way to look at temperature changes from the DTS data is not to look at the absolute temperature, but to look at the temperature change from the reference trace. So the reference trace here is defined as July 15th at 12:15 p.m. Okay, so that becomes your reference. So every trace on this waterfall plot is the change relative to that. Now, what you see here is that you started pumping here on the 18th at 2.5 barrels per minute. And maybe this shows you a little bit better, Joe, that there's actually a kind of a delay in the temperature rise above this deep zone. But look what happens way down deep. It actually you have cooling relative to the baseline. So it's almost like that fluid. I mean, it's making its way over. That cool fluid that you're pumping is making its way over, and it's colder than it was before as it comes up that 16B well. And you see it climbing. I mean, it's climbing up the wellbore over this time period. So maybe that is the circulating fluid here, right? And then above it, it's warm. So maybe it's that cold fluid is acting like a plunger again. It's pushing the hot fluid up to 16B well. Okay. Okay, that whole process of crosswall circulation can also be looked at using RFS DSS strain
If we
change.
go there, there was
Yeah.
another question. It looks like
Where do these questions come across? I don't.
you can occasionally see him up there.
Okay. Want to read them out to me there, Sean, or?
I'm not seeing anything.
Oh, okay. It may have been the last question or
Let me just see this chat here.
oh, I guess not.
Yeah,
Maybe it was
okay.
the older
Yeah.
question.
Right. Okay. So another way to look at the thermal characteristics during this crosswell flow is not to just use the Raman DTS method, but to use the RFS DSS method. Because if you think about the theory that I talked about this morning, the delta, the frequency shift is a function of both mechanical strain change and thermal strain change, right? I mean, a piece of glass in there is going to expand or contract based on mechanical, but also thermal. So under a condition where you don't have a lot of mechanical strain going on, like active fracturing, most of it's going to be driven by thermal strain. So in this particular use case, we can look at the DTS data or the RFS the RF Rayleigh frequency shift strain change data as a thermal detector.
Yeah, so it's relevant to point out too, that when you were showing that diagram of the deep cool inflow.
Yeah.
That's before the rest of 16A had been stimulated. So that
it
was only when the toe and the two shallower intervals had been the stages 1 through 2 and 3
Yes.
were for transmission of fluid.
Exactly. Yes.
So that explains precisely why it's limited to the bottom.
To the very bottom, right? Yeah.
Yeah. So you'd expect that to change once you had the other stages through 10 available for fluid.
Yeah. Okay, so if we look at the RFS DSS measurements during that same time period, same story. It's consistent with the DTS data. What would be different? The spatial resolution on the RFS DSS data is 5 times better on the RFS data, if that matters, right? It's 20 centimeters versus 1 meter. And the time sampling on the RFS DSS data is faster than the Raman DTS data. The Raman DTS data, you get a measurement about every 5 minutes. Here you get a measurement about every 70 seconds. So the speed is faster, the resolution is better, and this is what we see. So here's a waterfall plot of the strain change relative to the baseline, which is back in here. And you can see that as soon as you start pumping on the well bore, you get some positive strain change. It means that, you know, things are expanding. So you don't, at least in this, you don't really see a lot of the cooling effect, as well as you did on the other one. This is similar to what these are depth traces from 7,000 to 10,000. You can see the Rayleigh frequency shift strain change increase at these different depths pretty rapidly after you start pumping. I don't know if they're pressuring up here. You almost see that break in the slope before they start pumping at 2.5 barrels a minute. I don't know why that is. I mean, maybe maybe the pumpers gave us a time that was slightly off. I mean, that's possible. I don't know. Or maybe they're doing some pressure testing, and it actually, you know, if you're pressure testing the well, you're not actually pumping fluid. It still has connectivity to the reservoir. So maybe you're moving fluid through the reservoir even with a pressure test. Okay, so now if we take this data and this is the cumulative strain change. If we differentiate across time every one of these traces, that's the strain change rate. It's the strain change rate of change. It's just the time differential. So we call it strain rate. So what that looks like is this. So now, there was a PLT in July of 2023 before the circulation test was done. Do you remember that, Joe or Kevin? There was a small circulation, there was a PLT run in the 16A well?
Yes.
Or maybe
Yeah, we ran PLT in the 16A well.
right. Okay, so there's a PLT run in the 16A well, which is it produces pressure in the 16B well, right? I mean, you're pumping and everything like that in the A. I mean, this strain change rate data shows how closely connected the A and the B well are. I mean, you can see these effects on the B well. So Kevin, was there no PLT run on the B well also?
No, not at this time, because in the B well there wasn't any perforation open. It was just the open hole.
Okay. So what's interesting about this is when you're working on the A well and you're kind of creating an effect of fluid change on the B well, look where all the positive strain change is. It's down in that deeper zone. I mean, this is indicative of hot fluid kind of moving in that B well. All this red stuff here, and it even has some slope to it. Like it's actually moving up the wellbore. You can see that on this data.
So the only place that fluid can enter the B well is through the open hole. So
yes,
below where the fibers terminated.
Exactly. So the origin of these signatures is actually, you know, below where we can see.
Yeah.
But it's moving up and into the case section where the fiber exists, and we can clearly see it. I mean, it's not overly indicative, but it does tell you that even working on the A well, you're moving hot fluid up into the B well.
Yeah, the other thing to remember on that, Dane, I think is, you know, you're injecting into the A well at different rates, at 2.5, 5, and a little bit above 7 barrels a minute, but the flow rate into the B well was only in barrels per hour. So the rate was not high in the B well because there was so much fraction volume that, you know, needed to be filled up before we could really establish good circulation.
Yeah. Well, certainly you don't see much slugging. Slugging is usually indicative of fast movement up the B well. You see a little bit of evidence of a slug right here. You see this red line that's kind of tracking up the wellbore. That's a thermal slug, but it's not moving fast and it's pretty weak.
Yeah.
So there is some thermal slugging, but it's not very significant. Here's a real slow one. You see this way up in here? I mean, that's some type of a feature that's just creeping up the wellbore. Those are called thermal slugs. And you can only see that stuff with this kind of data because it's so sensitive of temperature, and it's such fine spatial resolution that you can see these little slugs.
So why the color were we changing rates here to go from, so where your arrow is, red, blue, green?
You mean this here? Yeah, I mean, they're changing the rates on their pump down over on the A well. So, I mean, because
Yeah,
these
the rates are
systems are so,
changing, rates are changing on the A well, but it's, the rate changes aren't really so indicative on the B well. You just notice on the B well that the rate of flow into and up the B well continues to increase during the pumping into the A well, but it doesn't happen in steps.
okay, so let me just move on then to, so that's the PLT stuff. That wasn't, so this is the PLT time zone that we were just talking about and what we see there. But beyond that, then there was a break in time, and then they did some circulation testing from the A to the B. So from this line forward to the right is when they circulated on the A or pressured up on the A and did some circulation work. And this is the response on the B well. So now, rather than just kind of seeing these shadows of heat or slugs, you can see them much better now in the deeper well. You see these red blobs in here. Move this thing out of the way. So, this is the hot zone. You can see it during the PLT work over on the A, and you can see it during the circulation from A to B. And so that all looks normal, kind of like what we expect. What I don't understand very well is that, even back here on the circulation or the PLT work, you see a little bit of a heat feature right at the shoe, right at the intermediate casing shoe on the B well. And that slug slowly moves up, and then when you start pumping on the A well again, it pushes it up. So again, I just point this out that there's these anomalies that are occurring that occur near the 16B intermediate shoe that seem to create some features in the data. I mean, this feature here, this slug is not emanating from deep. It's emanating from where the shoe is on the B well. And you see it again here during the second phase of the circulation test. It happens again. So
We practice in that time.
yeah, I think that I'm not going to say why, but I just want to point it out as an observation.
Well, we have core firm right there. It is fractured and sheared and altered as can be.
Right there. Okay. Well, that might be important.
There's another, sorry, go back to that. So there's another thing. So the flood engineer was analyzing for chloride, and there are fluctuations in the chloride around that time. And I kind of think, so that's an early morning, that what you're showing there, that far right, July 20th,
Yeah.
like 2 to 3 a.m. in the morning. That one, no, keep on to the right, that one right there.
Yeah.
That's like after midnight.
Yes.
That's when you and AT were up late in the morning, or late at night.
Uh-huh.
And so there are some anomalous chloride pulses that came through. So
Yeah.
I'm just eyeballing this, wonder.
Yeah, that's 1 to 3 a.m. right in there on the
Yeah,
20th.
so that was some unusual spikes in the chloride chemistry.
And that heat goes all the way to the surface. I mean, there's the wellhead right there. This is all depth calibrated. So, I mean, all that stuff coming from there, you can see it slugging right up the wellbore to the surface.
There's no way to get into the wellbore. What doesn't have to be in the annulus?
Good question. I don't know. I don't know how it would get into the annulus. I have no idea. I mean, this fiber response is in the annulus. This is not inside the wellbore. But if you guys are seeing some type of, I mean, this response, if this is actually slugging up the wellbore, this is fluid moving up the wellbore. So it may be because it's open hole.
That I understand. The second contribution,
Yeah.
I don't get it.
Right.
And it starts at the same time that the deep one does, so it couldn't be related to deep inflow evolving upwards. It's a separate inflow, as you point out.
Yeah.
Well,
I mean, maybe the source of it is, I mean, maybe the source of that's way down here at, yeah. I mean, that's about where the shoe is. 5,500 feet. You can see that it's a little bit janky the whole time. You see all this kind of this chatter in here. I mean, that's not just noise. There's some type of signal in there, right at that depth that's occurring over time. I mean, these little features in the data mean something. You know, you got a little positive strain feature there where you got nothing around it, and then you got this chatter, and then you got this slug, you know, a hot spot, and then this slow slug comes up, restart, comes up again. I have no idea how it could get. I mean, you know, maybe, you know, casings are not, maybe they're not perfect barriers. I mean, you got coupling and everything else. And
But when we see something at the surface, right? If this second aliquot of heat's coming in at 4,500 feet, traveling up the well, like if it was in the annulus, I'd expect it to leak out of the annulus. Like that. It can't get into the casing. Shouldn't be able to get into the casing.
yeah, I mean, but your chloride samples were taken from the fluids inside the well bore, inside the casing string.
Just pitch it out.
Is that right?
yes,
Okay, so why don't you think that those elevated chlorides or what chloride anomalies aren't coming from down deep?
I'm saying there are two tracks for heat coming in.
Yes. Yeah.
Deep and the shallow.
Yeah.
The shallow one's just blowing my mind, and I guess I'm thinking out loud. Like,
Yeah.
wow. There can't be a contribution from chloride there. There appears to be a contribution from heat. If it's going all the way to the surface,
Yeah.
then why don't we see a manifestation of that at the surface?
How do you know you don't? You don't have a thermometer up there.
We don't see the cellar filling up with water, for example, or like where's the flow exit at the surface if it's in the annulus?
Oh, I see what you're saying. There's no outflow at this time.
Exactly. Well, there's outflow from within the case, not from the exterior, unless it went out in a shallow formation. So
Well, no, but okay, I think the flow and heat inside the pipe gets transmitted through that steel easy.
Right.
So you could have all these heat signatures that you see on this fiber could be inside the pipe.
the graphic that you shows a time start that coincides, you know, with that dashed vertical line where your tip of your arrow ends, and I think that's what seems difficult.
that's what's confusing.
If that was a little bit delayed in time,
Yeah.
then yes. But it looks like it's happening starting at exactly the same time, and you've told us how good your timestamp is.
Yeah.
So-
Yeah. Oh, it is. Yeah. Do you mean it's starting at the same time as the deeper one?
So it couldn't be the deeper fluid evolving up the well.
Yes,
separate.
there's no move out on it.
Yeah.
Yeah, right. Well, you can see the precursor to it here too, Stuart. I mean,
Agreed.
yeah, there's
We do
precursor.
agree.
Yeah. I don't know.
I have a few questions in the chat. What the first there is the cement loss zone somewhere near the shoe?
What cement loss?
Yeah, I don't know where cement loss might have been. There's no way to actually tell.
Okay. The next one is was 16B choked?
During what? During this
Thank you.
period that we're talking about here? I have to go back and look at the data. I don't remember.
Yeah, I was going to say on our OB logs, that was, I mean, I only showed one page of the OB logs. Sometimes we'll have that kind of info in the OB logs. That was on the 18th. I mean, according to this, on the 18th, 18th, let me see what time that was. Of course, we always run into this issue in my so I think I'm on GMT time here. So I'm on the 20th, and I'm just after midnight on the 20th. So now that those OB logs are way back in here. So I don't have this. I'm not showing this second round of OB logs. They're just hidden in this presentation. But that data is available to know whether or not that 16B was open flow or not.
So what time are we talking about, Dana, actually, on the 18th?
Well, we're talking about on the 20th here, this zone in here.
It was flowing. I was there.
Okay.
Almost a choke.
Throttle back. We were maintaining wellhead pressure, I believe. So
There were, yeah, there were.
there was some back pressure maintained the entire time. But
Yeah.
It was flowing.
Okay, the next question is, did you monitor pressure on the intermediate casing annulus?
Can't, there's no place to measure it.
No.
Okay,
So that's no.
and then the last question is, how, I think this is referring to what Stuart was talking to, but how do you know this is not strain?
Strain doesn't usually slug slowly like this. That's usually a thermal signature. I mean,
Yeah,
how would
this is Doug Blankenship. I just real quick, the reason I'm asking, I asked if it was choked is so you start flowing into the well from 16A to B, you pressure up the system, and let's just pretend like you got a really crappy cement job above 5,000 feet, and you pressurize the well bore, your casing stretches.
It balloons
That's
a
the
little
reason I'm asking. Yeah.
like a balloon, yeah. Well, yeah, kind of a thermally driven, not a thermal strain, but a mechanical strain due to the choke back.
Yeah, that's my question. I have no idea.
Well, I mean, that's
just wondering.
Yeah. I don't know. You see where my arrow is right here? This big-headed black arrow. You see how it kind of, I don't know, it looks like it has an origin point and then flows up. It just seems to me like if you were ballooning the intermediate casing string, it wouldn't kind of have that origin point and then a flow upward like a move out. You know what I mean? It looks more like a fluid response, a fluid flowing response to me. But maybe it would maybe the balloon would start down there at the intermediate shoe and work its way up and look like that. I don't know. Okay. Can I move on there, Sean, or were there any other?
Yeah, that was all the questions in the chat.
Okay. Doug, did that answer your question or?
Oh, yes, sir. Thank you.
Okay. So you can dig into this data during that initial data. This is the pass on 2-day circulation test from back then. And it's just those 2 periods of time. And this kind of gets a little bit into the question where there's information on the 16A inflow and outflow rates that were measured, the pressures, and the temperatures. So, for instance, you can look at the 16B wellhead pressure as a function of time, and you'll see that there was, I mean, if the gauges were working at the surface, at least, there was no anomalous pressure that was detected during this during this period when we have this feature that's kind of moving in from that intermediate casing point. Right there. You see where that slug is that we were talking about? I mean, I don't see anything on the pressure. You can also look at the 16A wellhead temperatures and the 16B separator pressures. And you certainly see the separator on the B coming up right during that time frame. And you see that deflection right there? So that's what makes me believe that it's a thermally induced strain from fluid. I mean, it looks small, but it's definitely noticeable. Should probably take the derivative of it to kind of find that change point. Okay. And here's just another view of it. Where we kind of zoom in to the lower part of the well section. That um, just zoom.
Sounds like we might be having some technical difficulties. Dana, I'm gonna, let's just pause for a second. Let me walk down there. Hi, everyone. We'll just maybe give a minute. Dana's got to log back in. If it takes too long, we may just take our lunch break. So just give me a minute, please. Hey, Dana, are you back now?
Okay. Can you hear me?
Yeah, I can hear you now. Okay, so I don't know if you wanted to finish up that last slide or if you had anything left, but we can take our lunch break, or you can wrap up the slide, whatever works for you.
Yeah, let me just wrap up here. Oh, what the heck happened here? Okay. Uh, it's like my screen there that I want to show is just minimized.
Okay, I'm gonna walk down. Hold on.
All right, thank you. Unintuitive thing.
Did you want to switch to back to PowerPoint or?
Yeah, I just want to be able to show my screen. It's like right there. It's about as big as my fingernail.
So I should just be able to switch back over.
Okay. And can I put it in presentation mode then?
And then we may have to switch back to,
Okay.
yeah, hit the display settings again. And duplicate.
Okay.
That was a weird like black light.
Okay, so let me just finish up by saying that in addition to DTS and RFS DSS measurements that were being made during this first initial circulation test, we also recorded with DAS, distributed acoustic sensing. And one of the tools you can use for DAS is to look at the very low frequency components of DAS. And the LF DAS components it's a strain detection tool. So again, if your fiber is being affected by thermal strain because of fluid inflow and up the well bore, then you can use low frequency DAS to see that rather than looking at acoustic noise. So that's why a lot of people say, oh, you can use DAS as a strain tool. It's true, but you have to know how to take the full bandwidth DAS and get down into the sub 0.1 millihertz or sub 0.1 hertz range to actually see anything of value. So here we can see the inflow, the thermal signatures of hot water inflowing into the 16B well during the 16A circulation test, both on the first round of that test and on the second phase of it. So it just reiterates or just kind of corroborates what we're seeing on the RFS DSS data. Another reason that DAS was recorded during the circulation test was to surveil for microseismicity that may occur, right? When you start moving fluid between these well bores and there's existing fractures and faults, there's always some concern of induced seismicity. So that microseismic data was collected, but this data was also, the DAS data was also used to look at this low frequency strain response that's thermally driven.
Yeah, but there are no perforations. The only way into the well at this point is through the bottom.
It's through the bottom, yeah. No, but let me say this though. This well has fluid in it. The 16B is not evacuated.
True.
There's fractures all through the bottom of 16B. That's proven by the microseismic that was attained when they fracked 16A. So if you start moving fluid from 16A to 16B, you can heat up around that wellbore, wherever those fractures are. And then that heated fluid will heat up the fluid that's inside the wellbore, which will want to move up whole, especially if that wellbore is open, right? It'll move up just from thermodynamics. So I think that's what's going on. These are not perforated inflow. Of course, there's no perfs, but there's fractures all around that well. It's proven by the microseismic. And those fracture fairways must still be open between A and B a year later.
Okay, so we're seeing maybe our cased off fractures from the stimulation contributing heat. So this is okay.
Yeah.
I'm following it.
Yeah, that's what I would say. Because yeah, absolutely, they're not inflowing through holes. Yeah. Okay, so that kind of ends just kind of that first part there where we talked about evolution 0 and 1, which were cement monitoring, and then circulation test 1. What I'm going to talk about next, right after our lunch break, is hydraulic fracturing of 16A, as seen at 16B, a lot of geomechanics in there, and then the 16B frac and the kind of the injection allocation work that was done. So when you're measuring on a frac in well, you're not measuring any kind of, the frac response in the far field. You're just measuring the fluid that's leaving the perforations. So that's called an injection allocation, and it's a proxy for knowing how well you might be fracturing. But in this case, see, what we're really trying to do is we're trying to connect the fractures between A and B. So if you start pumping on a perforation that you put into granite in the 16B well and you can't get any fluid into it, it means you missed the hole. You missed the fracture. Right? You probably, but if it's taken a lot of fluid, you've probably connected up to the fracture that you've already built from the A well. So we'll talk about that in a few minutes. I don't know, Sean, am I going to be talking through lunch? Is that what we want to do here, or are we taking a break?
Yeah, let's take a break. I'm sure everybody could grab some food or do whatever. So I don't think anyone wants to miss anything. So
Okay.
how about we break till 1 o'clock and then we can pick back up then. So
Okay. Thank you.
okay. Thanks, Dana.
So I gotta
Hi, everyone. We'll just get started here in a few minutes. That looks good, Dana. Hey, Dana, can you hear me? I think we're about ready to get started. If you are,
How can you hear me now?
yes, I can hear you.
Okay, good.
Okay. Yeah, we're 12:59, so whenever you're ready, go ahead.
Okay. I'm gonna go right at one, so just give it a minute. Okay, I am going to get back into it now, and what I'm going to launch into is kind of a review of the hydraulic fracture monitoring of the 16A well. So we call that the injector well, 16A. And just refresh, 16A stages 1 through 3 had been stimulated in 2022, stages 1 through 3. And I think that the location of the 3R stage was close to the stage 3 from 2022, and then we stimulated up through a stage called stage 10. So these operations occurred in April of 2024 this year. And just again, if you weren't on earlier, I'm Dana Jurick. I'm the Chief Operating Officer of Neubrex Energy Services here in the U.S. Key contributor for all the processing results that you'll see here is from Dr. Arthur Guzik, who's our software engineering and services chief out of Neubrex Impra out of Baden, Switzerland. So let me just see if I can move my thing here. Just to start with our acknowledgments, if you weren't here earlier, you know, this is worked under, all the work at Forge is done under US DOE grant, that number, Enhanced Geothermal Systems Concepts, Testing and Development at Milford City, Utah Forge site. Certainly, we're thankful for the stakeholders in the area in Beaver County and here in Utah, and the people involved in supporting this effort. All these field operations were supported by, you know, numerous people, Alan Reynolds, Leroy Swearingen, on location, Kevin England, who's on this call today, John McLennan, Joe Morris, Garth, Monty, Dr. Sharma at UT Austin, Ben Dyer and Peter Meyer from Geoenergy Swiss, my Neubrex ops chief, Wayne Fishback, who was in the field for much of this time. And then the crews that were doing the work, frac drilling, water management, HSE crews, and so forth. So we're thankful for all those people and want to acknowledge all their efforts. Okay, I'm going to just start out with the schematic here that thinks about how you measure the far field strain response to a hydraulic fracture, which is the situation we're in here, because we don't have a diagnostic measurement tool in the 16A well. We only have it in the 16B well. So if you're in the 16A well, over here on the left, you have a casing string, like 7-inch. It's cemented in place. There's a fiber inside of that cement sheath, coupled to the reservoir. Not in this case. I mean, in this case, we don't have a fiber in the treatment well or the producer, but we're putting perforations into the wellbore. So each grouping of perforations is called a stage. Below the perforations, there's a temporary plug set, the toemost cluster, and then you pump fluid under pressure and slurry under pressure down the wellbore. It can't go past the plug. It's not supposed to go past the plug, or leak downhole through the cement sheet that's supposed to go out of the perforation clusters, which are holes in the casing string. That process creates hydraulic fractures that move out and away from the wellbore. So in this very simplistic cartoon, there's a fracture that moves out of each cluster towards, in this case, towards the monitor well. So here's our 16B monitor well. There's a fracture tip that's propagating forward out in front of the tip of the fracture is this thing called a cohesive fracture process zone. It's not actually, it's kind of a strain zone before the frac is able to move through the rock. Eventually, the fracture process zone and the tip intersect the wellbore. And that is what's detected by the fiber optic, you know, because you've got, in this case, mechanical strain that's occurring, and it can either kind of dilate or extend the length of the fiber or compress it, depending on what's happening in that fracture. And then the fracture moves past the plane of the wellbore, and you don't see it anymore unless you've got other observation wells. In some cases where we've got multiple observation wells lined up with fiber, we'll see the fracture hit one well, propagate, and then hit the next well, and so on and so forth. And we can calculate fracture propagation speeds and how the fracture is, you know, branching and things like that when we have multiple observation wells. So just a thing that when I was trying to learn about fiber optics and what I was seeing in the data, I came upon this idea of slit scan photography. And it's kind of an important concept to understand when you're looking at fiber optic data plot analysis. I'm going to stop right there. that is a slit camera image, just like they used to use these in horse racing. They use them in track and field. This is the moment in time when each runner crosses the finish line. So it's not space that you're looking at here on the x-axis, it's time. So time is increasing to the left. So Usain Bolt, you can see how far out in front of everybody he crosses the finish line right here, second place here, third place here, and so on and so forth. I think it actually, you see if I can move it up a little bit. So that's the concept of slit camera photography. Now, if I go back to the presentation, so here's what we normally see with our eyes and with the camera is everything's moving in space and across time. But in slit camera photography, you get these snapshots that are being taken very quickly that shows you when the runners cross the finish line. So you can think about the finish line as the well. And if we go to an actual data set that I collected where there were multiple clusters in the treatment well, and there was an offset horizontal well that had fiber in it. So once the ball seats in the treatment well, then you start pumping fluid through those perforation clusters. So this is like the starting gun. And the fractures are moving towards the line. And you see this zone out in here, kind of this yellow reddish. This is fracture process zone. No tip has hit the well yet. Eventually, the tip, there's a fracture process zone that's running out in front of the tip, and then eventually the tip crosses that well right there. So this is the winner. This is the fracture plane that first hits the well, then second, third, fourth, fifth, and sixth, and so on. So like I was talking about this morning, this is a waterfall plot. Depth along the horizontal, time, where time is actually increasing to the left in this case, and then an associated pump curve data set that's tied in time, GPS time stamped. So now, if we want to map where the fractures hit the observation well, I can pick these depths, these exact depths. So now I know where the fracture planes actually hit the monitor well. Okay, so this is a way to map a dynamic. You can not only can you map where they hit, but you can see how they evolve through time. I mean, it's very interesting that each one of these little fracture planes actually has a fracture process zone in front of it. And then you see this red here is extension. So in this case, you have two horizontals. The frac is propagating towards the horizontal well. So when it opens up, when that fracture plane opens up, it's extensional, positive strain. When you have positive strain around a fracture that's trying to extend, what happens around it is it compresses the fiber around it. That's called the strain shadow. So this blue on either side of the tip on each one of these fractures is the strain shadow around the tip. So the tip, the fracture process zone, the tip, and the strain shadow around it helps us identify where we actually have fracture planes that are intersecting wellbore. And thank goodness for this slit camera photography and Usain Bolt, because it helped me understand how to kind of really interpret all of these things. So this is evolution 2. So we've talked about cementing, post-cementing, circulation tests. Now we've gone to April of 2024. We're going to start frac stimulating the 16A well, and we're going to watch it from in the far field from the 16B well fiber, which is above the 16A, right? In this case, we're not horizontal. We flipped it on its side. 16A well is low, 16B well is high. And the primary method that we're going to use to make these observations in DFOS, distributed fiber optic sensing, is the Rayleigh frequency shift distributed strain sensing method. You can also do this with DAS. So if you take DAS and you take the low frequency bands of DAS, as I said before, that's a strain detection tool. You can use that to measure the strain that's evolving through time also. One difference is that the spatial resolution on the RFS DSS for the strain monitor is 20 centimeters, very high. It's like buying an HD TV, a lot of pixels, you know, you can see so much detail. The spatial resolution on the fiber for DAS is 1 to 2 meters. So 5 to 10 times coarser. The pixel sizes are 5 to 10 times coarser than they are with RFS DSS. When you're looking at images, that matters. You can see a lot of detail. What do you give up? If the strain is evolving very quickly in time, if the changes are very quick, DAS is a better tool because you know you're measuring that slit camera photography is almost more like a movie. You can see it evolving really quickly. If you use RFS DSS, you're getting a measurement about every half a minute, every 30 seconds. So from what I've seen, it's adequate. That spatial sampling is adequate because the fracture evolution is not instantaneous in time. It evolves kind of slowly.
So has that been done? Has GES done that kind of analysis?
Not that I'm aware of, no. And I haven't either. I haven't taken the DAS data that was being collected for microseismic data and then focused that on the strain. You'd have to filter it back at the low frequency strain component and look at it, but I haven't done it. Okay, just to recap again, review here. Here's the wellbore geometry setup. Just to reiterate, you know, this is to the west, the well, and then the wells are drilled at a 65-degree slant towards the east, with the treatment well 16A underneath of the 16B. There's a couple of vertical monitor wells here that were also laced up with geophones collecting microseismic data during this process, in addition to microseismic data that was being analyzed on from the treatment well. Okay, so there was a design for each one of the stages of the 16A treatment well from 3R, where they define what that treatment stage looked like. You have the open hole section plus cluster 2 and cluster 3. They tell you the plug depth. So there's a plug depth set below these clusters. Okay, that was at 10.095. And then stage 4, 5, 6, 7, 8, and 9. So all of these cluster depths and plug depths are predefined before the job starts. Now, when you pump a job, you capture data from the pumping company, and these are called pumping curve data, pump curve data, where you amongst other things that they measure and record, they look at treating pressure, they look at the slurry rate that's being pumped at surface, and they look at the proppant density that's being injected into, you know, of the slurry. As a function of those measurement types, you know, pressure, rate, and density, and time. So we know when they pumped every job from 3R through stage 10 and what those stages look like. Of course, this is all locked in time, so that means we can associate it with any fiber optic measurements we make. Excuse me. So, waterfall plots. This is an RFS DSS strain change waterfall plot. What that means is that there's a reference profile back here, early time, which becomes our baseline. And then every 30 seconds or thereabouts, we take another profile and we compare it back to the reference profile, like we've been talking about. So then we can measure the amount of strain change. This has been converted from optical units into strain change value in microstrain units. So this is the amount of strain change that's occurred as a function of not only time, but also along the depth axis. So then we know the start time, we know the finish time of each stage. So we know that this, for instance, and we know where it was pumped on 16A, we can determine where the frac hit occurs on 16B by this plot. So like right here, this is where the frac, where the frac energy, where the strain energy intersects the 16B well for stages 3R right in here. Then there's a delay time because they got to pump a wire line down, set plugs and make perfs. And then they start up with stage 4. There's stage 4, stage 5. You'll notice in this particular case, it stages the crosswell fracture-driven interactions. That's the new term for frac hits. They lay right on top of each other. They found some fairway, some zone of weakness or fracture pathway that they didn't create new hydraulic fractures each time. I mean, maybe stage 3 was a new hydraulic fracture, was never there before, but stages 4 and stages 5 find it again. Stage 6 was kind of an aborted frac stage. There's a little bit of strain that hits above, heelward of the 3R, 4, and 5 stages. And I'll show you this a little bit clearer in a minute, but it's right. Stage 6 hits here. The strain from stage 7 occurs over this depth range. You see it here. Here's start of stage 7 to the end of stage 7. So all that strain energy in there, uphole now, up the 16B, occurs here. It's interesting that even after they quit pumping, there's a little bit of frac or strain energy that occurs right in here. I don't know, I don't know if Kevin is on board, but there was this little bit of treating pressure pump between stages 7 and 8. I don't know what that was about. I don't know if that was what maybe that was a 6R. They were trying to redo 6R. I'm not really sure.
Nope, sorry, Dana. That was pumping down the next frac plug.
Okay, pumping down the plug. So it's shown here, just like it was before stage 7. You could see
Right.
pumping the plug. And so there's kind of a gap in here, even though we're seeing some downhole strain energy. We go into stage 8, and this is really very interesting because normally strain energy progress as you move this series of stages from toe towards the heel on the treatment well. On the offset well, you see the strain energy, crosswell strain energy, move up hole with it, kind of lockstep. But in this particular case, even though stage 8 of the treatment well did move way up hole, the first frac hit from stage 8 moved like 600 feet up hole in the B well. It went way up here. That's the first arrival on the B well. And then it kind of, you get other frac hits, kind of the 2nd place, 3rd place, 4th place runners.
So was it chronologically moving down?
Yes.
Each one, it didn't go down and in between or anything?
No,
like that?
it chronologically moved down hole, but then later on, the next one will be more clear. It did jump up then in late stage 8. You saw it kind of go high again.
Oh, so it went back to where it started.
It did, yeah. I'll show you that with the strain rate plot where it's a little bit more clear. And then here's stage 9. It kind of what we call reoccupies. It kind of reoccupied where that major hit, that shallow hit, occurred on stage 8. But then you also get a more heelward fracture developing on stage 9. And then there's a gap in time. Stage 10 is pumped, and it effectively just reoccupies what stage 9 or stage 8 and stage 9 did. So that's just kind of an overview of the FDI's frac hits from stage 16 to stage well 16A to well 16B. I'm just going to note one thing here that I found interesting. I don't really know the meaning of it, but when we pump stage 3R, those perforations were down low in the 16A well. Most of the strain energy was seen down here at about 97, 70 feet, this fairway here. But there is a strain feature that occurs late in stage 3 that's much shallower. Like I think about 300 or 400 feet shallower. You see where my arrow is, and it kind of stays strained for all of those early stages and even into stage 8. And stage 7 actually is a reoccupation of this early strain feature. I have no idea how that could have happened, but the data is showing it.
Can we go back to that slide for a second? The first 3 stages,
Mhm.
we're showing that we don't see anything unless a fracture propagates. Do you see reactivation of fractures? Are they still gonna?
Yes, I'll show you this on the next slide here, the next few slides. An easier way to look at this kind of data is to take the time differential of every profile, right? So how much is the strain changing minute by minute, everybody, right? That's called the strain rate. So the strain rate is a little bit easier on the eyes to look at. So this is the strain rate data. So again, this is 16B. It's the same setup. It's just that we've kind of differentiated the data. And here's stage 3R. When you first pump 3R, you get this major feature that runs from the bottom of the fiber to the surface. Something shot up the wellbore. I don't know what it is. It's unusual. But these features here are the frac, basically. They look similar to what I was showing earlier in that example here, where you have a fracture process zone, a tip, a strain shadow, and then you often get these wings when the strain is kind of like propagating down the fiber length on each one. So that is a strain rate plot. These are strain rate plots, or a strain rate waterfall plot of all the stages, 3R through 10. And it's zoomed out right now. I just wanted to show here that you can see that we're working low in the wellbore, right? There's a lot of wellbore sitting above us. We're working in the bottom 20% of the wellbore, but there's a lot of good cross well far field strain energy that was detected on that fiber using this method for each one of the stages.
So is that something in the annulus? Do I have a crack in the cement against
With this one here,
the wellbore, that first one? See that?
I don't know.
It's the first time you really repressurize the well.
Yes.
So it's probably something that just is a reflection of pressurizing the whole well for the first time in a year.
Yeah, it could be. I mean, you're pressuring up, there's fluid moving in. It could be ballooning the whole well a little bit, and then it's just it's straining the fiber from bottom to top.
But I don't see that that shallower zone that you were talking about on the previous slide on this vision.
Yeah, because this is kind of instant. This is the instantaneous strain change. I think you can see it better on the cumulative strain change. We're going to zoom in. We'll keep our eyes open on that. Okay, so zoomed in now. Looking from 8,200 feet to the end of the fiber. The end of the fiber was still good here at 10,108. That was the original setting of it. So this is strain rate. So again, here's that zone you were just talking about, Joe. We kind of pressure up, right, and we get that effect. But then these are the FDIs from each one of the stages. And yeah, and you could kind of see there. So 3R, I mean, these are total reoccupations on those stages. Stage 6, when we pump stage 6, even though it wasn't a very great stage, they basically couldn't complete that job. I don't think there was any perf that really got, or prop that really got out. You still see a strain crosswell far field strain feature right here. I mean, it's pretty ugly, but there was something that crossed over. I mean, there was something that was created that hit the B well. Pump down the plug and then perf, and then you go into the 7R well, or the 7R stage. That's a really nice looking pump right there. I mean, you can see how, you got your pressure up. I guess that was that really a ramped proppant, or was it step?
No, there's no proppant pumped in stage 7 either.
Okay, so I think I had some bad data there on stage 7 where they were kind of showing a ramp prompting thing, but so it's basically just a slick water job, right? I mean, it's completely slick water, no problem.
Actually cross-linked.
Cross-linked.
Yeah.
Okay. All right, so that's cross-linked. And that is that's the best looking, normal looking fraction FDI that there is in this whole data set, because you see this wing out here. This is all the fracture driven interaction fracture process zone. That's the pre-tip fracture zone. You can see how wide it is when you look at it. I mean, that's from 9,300 feet down to really it's 400 feet wide. That strain front that's kind of out in front of the tip. And then the tip is right there, because you can see the negative strain right around it, right? Those are the strain shadows right around where the tip is, because the tip is opening and it's creating, extensional strain on the fiber, and it's squeezing the fiber around it. So we know where the tip is. And then we go into this craziness here. I mean, the fiber was acting very weird during this wireline job between stages 7 and 8. I mean, there's a lot of strange energy in here. It looks nothing like any of the other stages that we saw during the wireline runs. And then we pump stage 8, and this is where we get this huge change in where the FDI hits the 16B well. So I mean, that the tip there, and that first arrival is at 8,900 feet, and the first arrival tip on there was almost at 9,400 feet. So it's like 500 foot of change up the wellbore on where the fracture hits.
Can you show me that? Can you show me that again with your cursor?
Okay, so this is the tip arrive. This is the main fracture hit on the stage 7.
Yep.
And we pump stage 7. Everything looks good. There's actually multiple frac hits from stage 7. And
We're
there's
only showing 2, I thought, maybe 3. Okay.
Yeah, I have to zoom in. I mean, you see all these dashed lines in here?
Yeah.
These dashed lines are where frac hits have been picked on a close examination of the data.
Okay.
I mean, they're really close together, and you got resolution to see those close records. Then we do the wireline run with the plug and the perf guns between stage 7 and 8, and we get very strange strain energy up and down the wellbore, and it's not that much different than what we saw initially. I don't know what caused it. I don't think it's instrumentation problems. I mean, there's some kind of ballooning or something up and down the wellbore that has occurred there. And then we pump stage, so that's finished. We set the plug and we perf, and then we pump stage 8. And as soon as we start pumping on stage 8, we get this very large fracture process zone. You see that? You see it right there. I mean, it's this big red wing here over hundreds of feet. But the frac tip it's way up here. It's at like 8,900 feet. And you can see where it's picked. It's, even above 8,900. The tip is right there, because you see the strain shadow, the major strain shadow around it. That's what defines it. It sits right in between, kind of in the crotch between the two, negative strain shadows. So that's the first frac hit. And then I'll go into detail, but then you progressively through time, the fractures, there's a fracture here, down here. They kind of fill in below that first one.
I think that's pretty fascinating. I mean, it's almost like a fan shaped, you create one fracture and then somehow the next one grows.
Yeah.
I don't know what the fracture mechanics of that is, but it's
Yeah.
very neat.
Snap, crackle, pop.
Snap, crackle, pop. It's the
Yeah.
Rice Krispies frac.
Yeah. I think there's a line missing in here because I'm pretty sure we also picked this one, but you do a decent job of kind of filling in that space over time during stage 8. And then you pump stage 9. I mean, there's, you know, there's a run in here, there's a wire line run in here, and you actually see some energy during that wire line run right there, kind of on the top of stage 8. You go into stage 9 and you get another big, huge whack. I mean, the frac tip is right there, and it's pretty darn close to where you stimulated, where that tip was on stage 8. I mean, it's like right in line. It's right there because you see this huge amount of compressive strain on the fiber on either side of the tip. Like it's opening and it's just squeezing everything around you. And there's multiple frac hits in stage 9, gap in time. Then you pump stage 10, and it just reoccupies what you've already done. It didn't move up hole. So the top of your fracture, your stimulated interval is just above 8,800 feet. The bottom of it here is right about 9,800 feet. I think I figured out it was about 1,100 feet of stimulation or something like that. So there's just another, you look at the stuff in different color bars. Sometimes it helps your eyes to see things. So that's just the same data with just a different color bar. I use different color bars. It helps me kind of make picks and stuff.
Is this telling us anything about, say, viscosified versus non-viscosified fluid? 9 was non-viscosified, right? Slick water. 8 was viscosified. Both
Yeah, I
propped,
don't have that information up here. I don't have that chart, on
Yeah.
fluid types there.
both propped.
Yeah.
I think.
And
Kevin
both
can-
same cluster.
Kevin can comment on this, but I think what you can learn more from actually looking at the treatment records, comparing the two.
Yeah. You mean these curves here?
Yeah.
Yeah. I think it's good to use them in combination, right? Because this is kind of one-dimensional way. You just have these
Yeah.
are time series. This is time and depth series. And you can see how the chronological order too. The chronology of how these things develop within one stage,
Yeah, yeah.
if you've got multiple clusters coming across, is it always the heel one?
Mhm.
If it's always the heel that hits first, it's telling you that probably the heel cluster over on the treatment well is taking the most fluid because it's getting there the fastest. So even though you don't have any information on A, you can make some inferences on cluster efficiency and fluid intake on A versus what you see on 400 feet away on B.
So it's interesting in 9 that when you see the screen out starting to happen, the increase in the pressure,
Yeah.
that you start to get that red zone developing. I don't know, that's compression or tension.
Oh, yeah. In here?
No, farther up. Or is that 10?
That's 9. That's 9. I mean, there's no doubt when you see screen outs occurring, you often see responses on crossflow with a little bit of a delay, because it's on A.
That,
So to go. Questions? Will you finish, John?
that screen out was starting to happen pretty close to the injection well, though, I think.
Mhm.
What's the screen out?
That means that you're putting sand into a fracture, but the fracture is no longer increasing in length. And so you pack proppant towards the tip of the fracture, prevent fluid from getting to the tip, and you inhibit propagation. And the pressure builds. It's just like filling a balloon after you've got a blockage at the tip.
And so the sand is screening the fracture too.
Yes.
I mean, where I see, look at this, John. I mean, look at the tip here when they're running out and they get this big pressure spike over here. I mean, it definitely correlates with this big positive strain.
But it looks like that also correlates with a change in proppant concentration. And hey, Kevin, what's your sense?
So I can't, I'm thinking that we didn't change proppant concentration towards the end because of the fact we were increasing pressure. I think we stayed at 1 ppa the whole time and never went to 1.25 or 1.5.
Did we go to 40/70? Or
Yes.
did we do it earlier?
Yeah, no, we did pump 4070. I'm not sure exactly where that started in the process of things, but my guess would be that the increase towards the end there was probably pretty much driven by the fact that 4070 was starting to go into the fracture.
Okay,
This is on 8 or 9?
9.
9.
So where you increase the slope of the blue line,
Yeah.
that's screen out.
Oh, yeah, yeah, you're screening out, right, yeah.
Yeah. So that's all happening pretty close to the well.
Yeah, and so the red zone up above is maybe a red area.
Yeah. I want to make two other observations on this strain rate plot, which is I talked about this little weird anomaly up here way above the actual FDI zone during stage 3. It's right here. I mean, it's not noise. That's real. That's real strain that's somewhat occurring, at 9,400 feet, even though we're at 9,800 feet where most everything else is occurring. And if you track that over, that's right where stage 7 occurred. So I don't know, maybe there's some zone of weakness in the cement or the formation right around 90, 94, whatever that depth is, 9450, that just pressuring up the well kind of produced some strain on the fiber. And then later on, you're hitting that same zone of weakness when you cross well on stage 7, when you pump stage 7.
I see Clay making notes. I'm going to ask him a question. Did you see anything with natural fractures at that depth or something that would suggest a feature?
I would have to go back and look at the FMI logs, I guess, in particular. See, but I can tell you off the top of my head.
Yeah. I mean, you see, and then it stays even active. You start pumping on stage 8, and it just stays active for. That's kind of some funny zone in there, right around 9450. So what you can do with all of this data is, if you think about this plot here, no, this one here, no, this one here. Sorry. If you pull a trace, this is a cumulative strain. This is the strain that's accumulating on the fiber through time. It's not the differential. And if you pull a trace out here somewhere late, you get all the strain that's occurred on the fiber over the entire period. So then if you take that trace, that profile, and you look at it like this is a little messy, but these are a bunch of cumulative strain profiles through time. And the latest one tells you where the most cumulative strain has occurred on the fiber throughout the entire 16A pump job at 16B. So if you pick all of these peaks, it tells you where the most likely fracks occurred, hydraulic fractures occurred at 16B, and they stand out. So what we did in the field was we went through and we picked all these. We just went to a plot like this in our workstation. We said, okay, bang, 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 bang. We just picked all of these things from H1 to H28. We picked 28 independent little features that the data showed us, and we we cataloged those features, and we picked their exact depths. 28 picks were made in the field. And then
Dana, sorry, can we just back up a couple of slides? I just have one quick question. That one right there.
Yeah.
Just to clarify, stage 3R, 4 and 5 seem to be all occupying the same fractures.
Yeah. Yes.
Correct?
Yes.
And can you just clarify that the blue that tails off at the end of each one of those stages, that's another stress shadow?
No, that's those fractures that are relaxing. So those fractures, when you have active fluid moving through them and they're dilating, they stay dilated. But once that energy passes through, they relax a little bit. So that's the blue. That's the negative strain change. So you'll see every one of these. Once you kind of let off the pumps, once you kind of quit pumping, you see how it goes blue. Let off pump, blue, blue, blue. Out here, there's some light blue in there. You let off pump here. So that's a common signature that you see after you you disconnect the pressure that's on that pipe.
Yep.
Yeah, okay. So then we picked all of these frac hits, and then, John and Kevin, myself, there was a whole gaggle of experts. And what we did was we said, okay, on 16B, we're not going to use a wireline plug and perf operation. We're going to do TCP. So we only have 20 guns, or maybe, and 20 plugs. So we have to high grade. So we went through this set and we said, okay, which 20 do we like the best? So out of the 28, we picked 20, and we used a variety of different tools that we have to kind of look at these crosswell strain hits to try to pick the best looking ones. So these are something we call frac logs, and it's a different way of kind of taking this data here and doing some integration work to try to figure out which ones are the most reasonable to use. Now, so I kind of jumped ahead to what we were going to do on 16B. I just have a few slides here of some other graphics that we had to help us understand the Crosswell FDI energy. And what I've done here is posted up. Here's the 16A trajectory here in the red. Here's the 16B with the MDs posted on there. And then these are the cumulative strain graphs posted onto that wellbore. So for instance, when we pumped stage 3R, I know where that crosswell strain hit. And I know that stage 3, 4, and 5 kind of all landed within a 50-foot interval on the B well. So I just kind of map them over there. And these are small cluster stages, so it's a pretty direct mapping. Here's stage 6, 2 cluster. I know where it hit. And here's the strain. You see it right there, that peak? That's the strain FDI from stage 6. And those things all move kind of like toward, from A to B, right? They got a little bit of a slant on them. And then you go to stage 7, and the azimuth of that propagation kind of flips. It kind of changes from going toward to a slight heelward. And this is all the strain energy. These little peaks in here, these gold peaks, those are the individual FDIs that you can see from stage 7. So those are kind of like the runners. Those are the runners coming down their lanes. They're crossing the finish line. We don't have the time shown here. What I tried to do here in some kind of cheap way was, this is time along this axis. This is depth down this axis. Here's the pump curve from stage 7. And so you see that line right there. It goes right through that first frac hit. So, and it's strong. There's a tip right there. This is the fracture process zone. This is the tip. These blue are the strain shadows around the major tip. And then these are secondary arrivals. All these little peaks are secondary arrivals that come in later. So again, it's similar. You have the heelward fracture hits first and it's strongest. And then the secondary fractures fill in below it. And they're coming in later and they're coming in weaker.
What's the difference in the yellow and green colors, say, just around your?
So yeah, if you think about this plot here, or maybe let me go back to this one real quick. You can pull profiles of the cumulative strain anytime you want down there, right?
Yeah.
And then that gives you a curve. That gives you the cumulative strain profile at any given time. So those different colors are just different time which we pull those profiles.
Oh, okay, got it.
Yeah.
No, I got
Yeah.
it. Okay, sorry.
So for instance, there was a certain point in time where kind of this secondary frac hit, it basically has the same maximum strain energy is that first one. And then you go to stage 8 and things start getting weird. Because even though I don't know where the actual origin point is, I know that some of the energy from somewhere in stage 8 ended way up here. I know where it hit because I have this data here. I have this data. So I know that the primary frac, the first frac tip hit way up here and it came out of stage 8, which is way down here. So there's a huge skewing now of the frac energy uphole. And then stage 9, I don't have a map, but they pretty much kind of covered the same range as what stage 8 produced right there. So that's one way of kind of looking at the data and understanding it in spatial coordinates and, knowing that, these are all the stage 3R, 4, 5, and 6 kind of hits right in here. Here's the 7 hits. And then the 8 hits are down in here plus up in here. There's a dead zone. I know that from about 9250 to, I don't know, 9100. There's a no man's land where there was hardly any fractures that occurred. So maybe that's something you have information on, Clay, in terms of why is that rock different, or maybe you don't see any pre-existing fractures in that zone. Okay, this is another way that we have 3D viewers. So again, here's the 16A treatment well, here's the 16B well, and we know where all the depths are, where all the clusters are on each one of the stages in 16A, and we try to just visualize where the energy goes on these different stages and what the strain looks like. So it's just what we were looking at a minute ago, but just in 3D visualization. Again, the point is that there's a rotation. There's a significant rotation in the pathways or the crosswell strain trajectories from the toe to the heel of 16A.
Where's the major fracture, Clay, down?
It's a major fracture at about 8,000 feet at 16A. So it's about what we're looking at.
And then here's another way to look at it too, just in kind of a 3D viewer, is that if you look at these alpha angles, which are the angle, it's the angle from like vertical to the what I call the FIP, the fracture injection point, to the FDI, the fracture driven interaction. That's your alpha angle. And you can calculate this alpha angle for each one of the stages. And you see how it, stages 3, 4, and 5, they're kind of, the alpha angle's about 20 degrees toward stage 7, and it's almost nil. It's like almost straight up and down, not exactly. And then you go into stage 8 and 9, and it just rotates, it falls over. So, something's driving that. I mean, I've talked to Dr. Sharma a little bit about it, and he was telling me he thought it was all just that he thinks there's a big, like a strain shadow or something around the stage 7, and that kind of just pushes everything, all the fractures, it pushes them, towards the west, because this is towards the west, right? Because the surface is up here.
I think that's unlikely.
I'm just telling you what he told me.
The reason I'm saying that is stage 7 wasn't pumped at a very high rate, pumped for a long time, but didn't put in a lot of fluid.
Yeah.
I'm going to say it's geologic control.
Mm-hmm.
So
I have a theory.
That's dipping west. Those
This is backwards, right? The toe is on the left.
That's right. Yeah. That's right. The toe is on the toe is on the east. These are drilled from west towards the east. Right. So yeah, this is backwards.
Look at south.
So which way the fractures are?
You're looking south into the board. Is that correct?
Which way would fractures be tipping?
Well, aren't
Well,
four to
Dana's
four
gonna
point-
interpret.
Okay,
I got, there's a blanket in front of some kind of animal. I'm poking my finger through there and I'm trying to figure out what it is right now. So I was, this was kind of driving me a little crazy and I had a little spare time on my hands. So I was thinking, what could cause that? So if the toes are towards the east, then this would be a downward, this would be some type of a fault. I'm not telling you what the degree of the dip on the fault is, but just saying if there was a fault or some type of a zone of weakness, I hesitate to say fault, but some type of a zone of weakness that goes down to the west and passes through both of the well bores, then maybe the early stages they follow that and they kind of rotate, they parallel that zone of weakness. And as you move up hole, maybe there's some anesthetics off of that you're crossing also as you move up hole. And maybe that's why everything rotates into a different orientation as you move up hole. So it was just the idea of a west dipping feature with some anesthetics that are east dipping. And maybe that's a geologic control line. I mean, it's complete hypothesis.
but presumably
We
there's a
thought,
conjugate system.
yeah,
Is there not?
and we fought west dipping
Well, but
fractures
this is showing conjugation though.
early on. In 58, west dipping fractures were a problem.
Yeah.
But we got east and west.
Yeah,
Well, I mean, this one here would be west dipping, and then these would be
Yeah.
east dipping.
Yeah.
This is cartoonish.
Yeah.
Because I tried to look at angles and stuff like that with my protractor on paper and stuff like that, and I just don't know. I didn't know what.
We're gonna get Dana, we'll get him a square or something.
I'm not square. I'm a carpenter, so yeah, I got squares and triangles and all kinds of stuff you don't even want to know about. Okay, so selected interpretations. Just some
But I think
interesting.
that slide's really important. I mean, those fracture corridors, the change in depth
Yeah.
moving along,
Yeah.
it's really strong
Yeah, it's
information.
right.
So I'll just throw out one other consideration on that, the fact that we're initiating these fractures from a 65-degree deviated wellbore, and your rate per cluster in the bigger cluster zones is much smaller. So there's a much better chance for the fracture to initiate longitudinally along the wellbore before it goes more transverse.
Yeah, I mean, the other thing that's not shown, I mean, it's very cartoonish, but you can see I have one fracture injection point on these stages, right? And that's
Yep.
not the case because I don't really know where the origins are.
Yeah.
It
But if
looks
you
on
go-
these longer, yeah.
If you go back to the one, Dana, just real quick, where you showed the strain along the wellbores where it shot up really quick. Yeah,
That one?
yeah. So, I mean, theoretically, that shooting up could be the fracture propagating along the wellbore initially before it decides it's going to find the right stress path and
Yeah,
propagate where it's supposed to.
right. You're saying specifically on stage 8. So
Yeah.
you could have, what you're saying is you could have had a kind of an actual FDI or interaction with fracture in the wellbore down here, but then it travels longitudinally until it finds a pre-existing zone of weakness and then shoots into it and then fills in subsequently.
Yeah, or it finds its natural path, where it's supposed to
Yeah.
propagate. But the problem is
Yeah.
with a 65-degree deviated wellbore is you're fighting that fracture to get aligned where it's supposed to be right off the bat because it's not perpendicular to the stress field that it wants to propagate in.
Well, there is some forward modeling that could be done to try to simulate what what type of situations would create that, so.
Yeah, I just think it's one to put out there and take a look at.
So I just had some, I mean, these are extra slides here, but this is just kind of some selected interpretations. We already saw this cumulative waterfall plot of the strain change. If you kind of zoom in, then you can see the individual stages in greater detail. This is why I say that stages 3, 4, and 5, they just reoccupy the same exact zone.
Can you make anything out of that vertical line at depth?
I don't know what that is. I don't know. It could be that I'm having fiber effects. I'm not sure what's going on there, why I have that. I don't know. Everything looks normal after that in terms of its response, but there's definitely a brick wall there. I'm not sure. Stages 8, 9, and 10 on cumulative strain. Again, you know, one thing that makes me question your theory, Kevin, about it being actual just transverse strain running up to 16B until it finds a wellbore is if you look at this diagram here, you see the arc nature of this light blue, and then it kind of goes up like that. That's a classical fracture process zone, you know, that kind of a shape. You know, so it doesn't necessarily smell like it's not vertical. What I'm saying is you don't have just fluid running up the kind of a cracked annulus or something like that and then finding a zone of weakness. It has shape to it. Well, I don't know.
No, I mean, it has to be, yeah, it has to be a fracture. It's not contained in the annulus by any means.
Yeah.
But it's a fracture. It's a propagating fracture, but it's propagating along the wellbore.
Yeah, longitudinally. Yeah.
Yeah.
Yeah, I got you. There's the regular plot we were looking at before. This is some work that we did where you can look at those fractures or those fracture-driven interactions in great detail, and you can kind of put those against your pump curve data. Of course, one of the things you can do is calculate your cumulative volume pumped at any given moment in time, and you can see how the different features of the fracture signal relates to volume pumped. And you know, that's often looked at as an indicator of things of importance. Like for instance, if this feature that we were talking about on stage 8 happened very early, like there was hardly any volume of fluid pumped before it happened, that probably has a meaning. And so, you know, all of these things, like, so what we've done is kind of catalog that. All of these event IDs here are features that I see a day. Those are reference numbers. Here's the date and the time, the total slurry volume that was pumped when those things happened. So, you know, doing some analysis on that kind of data to see if there's any patterns in it, you know, maybe we can get a data scientist involved and look for patterns in the data. So here's just a zoom into the same thing, right? So all these different reference features have treating pressure information that are associated with them. And here I've just tried to describe what those features are. And then chronological development, all of these different stages at their crosswell, in the crosswell evolve over time. So you can do some chronological development or analysis on each one of the stages. And it's just written notes here, really. I mean, it's, you know, how did it evolve? What did I see? You know, did it fill in from top down or the bottom up? So those we have all this information, and I'm not going to go through it all. And then back to our favorite stage 8 study, probably understanding the evolution of that thing out in front, that fracture process zone or that longitudinal frac. That would be a good study to do with some people that have some modeling capability. In whatever, you know, it's a geomechanical modeling problem is what it is. And then, so this is a little bit of this is the kind of detail you can do when you zoom into data. you can kind of get into each one of these things. You can study each one of these features in great detail against the pump curve data. You look for these heart-shaped features and what do they mean, and so on. So the data is rich. I think it's pretty high quality for further analysis work and modeling for data and trying to understand, trying to see if you can get a model to fit the actual observations. Okay.
So again, this strain data, the last one, these are strain data between 8 and 9, on the last slide before your.
Yeah. Oh. This one here.
Yeah.
Mm-hmm.
So to the right there.
Yeah. So when you're in between the stages, of course, it's not like there's nothing going on. You're pumping down plugs and perf guns between the stages. So you're putting pressure into that well bore. So there's perforations below. I mean, you haven't set the plug yet. So you're pushing fluid through those existing perforations down to the next plug. So if there was a zone of weakness or a fracture that was maybe nascent, you don't really stimulate on it until you're actually doing that plug and perf run. So that's why sometimes you see energy between the actual active pump jobs. It's not uncommon. You see, I mean, there's several of them. Look at this one.
Yeah,
yeah. And there wasn't anything there before. So, what that is, just going back to the track analogy, that could be a late finisher. I mean, that guy was not even he was evolving towards the finish line during stage 8. So he's there. It's just not until he got the nudge did we see him. And that nudge was the pump down of the guns and the plugs.
Well, I'm kind of curious if these are stress shadows as well.
Maybe
play into this.
Yeah. Possible. Okay, so that kind of finishes up the 6A far field crosswell frac analysis. So I don't know Sean, were there questions coming through? I didn't really see any or hear any.
Yeah, we just had one. It was a question around I guess, locating the origins of fractures. So the question is, do we have a spinner test or that can tell the origin of a fracture? And I'll expand on that. Is there any other tests possibly that we could consider?
I'm gonna have to let Forge answer that because I think, or Kevin, there were spinner logs run on the 16A. So they may provide some insight on that, but I wasn't involved in the spinner logs.
I mean, the spinner logs are run during the circulation test. There's no spinner log run during the fracturing. So if we're talking about trying to match up spinner logs with fracture initiation, I mean, there's no direct measurement of that. The spinner log during the circulation test simply shows which clusters fluid is actually entering, which can be indicative of which ones were fracked better than, which clusters were fracked better than others. And then, of course, the percentage of fluid going into them can be indicative as well. Plus, we haven't gotten all the analysis back from the downhole camera. Maybe it sees some erosion on those same perforations that are taking most of the fluid, and that would be indicative of where the majority of the prop frac treatment would have gone.
Okay, so I'm just going to kind of segue into that comment by Kevin, because after the 16, no, this is not true. Hold on a second. Confusing myself here. Let me exit this. Find the next one. So the next thing that was done was the 16B stimulation, right? So we finished the 16A and stimulation, and then 16B was stimulated. And, of course, we're not looking at crosswell strain during, just see this more. No, it's not what I want. want to put this into this mode here. So when you hydraulically fracture the 16B well, the objective was to put the perforation clusters at points along the 16B well where we saw good, fracture-driven interactions from the 16A frac, and place them there and then pump into them. So you don't have a far field strain tool to measure during the 16B frac. What you do have is a fiber in that wellbore that hopefully you don't blow through with your perforations, and then measure the injection allocation into each one of the perf clusters. So in order to do that, because you're talking about fluid dynamics now, you don't want to use Rayleigh frequency shift distributed stain sensing because it's too slow. So what you do is you use DAS, which is recording at like 5,000 samples per second, and you're trying to watch acoustics and noise and that kind of thing around the 16B well. So this gets down to DAS-based frac fluid injection efficiency. You want to know how efficient the fluid is leaving the fracture injection points. You want to make fluid allocation estimates on a relative basis per stage. If you've got 4 clusters on a stage, for instance, do they treat evenly? Or is one taking it all? Or is it the toe? Is it the heel? How is it distributed? So DAS can help you do that. And then the other important thing probably for you guys is plug efficacy. How well are these plugs that you bought holding when you start putting pressure on them? Because if a plug leaks or slips, then what you're doing is you're basically treating the previous stage instead of the stage you're on, and you're losing efficiency. So plug efficacy is an important thing that you can look at with this type of analysis also. Okay, acknowledgments, DOE funded, we appreciate that. All the stakeholders in Beaver County, Utah, Governor's Office, and the congressional delegation, thank you very much. And then all of the field personnel that were involved. It was a big group of people really contributing here. Okay, 16B, here's the design pump schedule. There were 5 stages designed. In the end, I'll just tell you up front, we only perfed and plugged and pumped 4 of them. Stage 5, we perfed, but we did not pump. So there's 4 active stages here. Here's the number of clusters per stage, the fluid type, total volume, design pump rate, 100 mesh, 40/70 volumes. This is the actual. So sometimes the actual and the design don't always match up. They're not too bad here. You can see that there was one thing that stood out to me on stage 2. They pumped 102,000 pounds of 40/70 instead of the plan for 63. I don't know the reasons why these variations, but Kevin would know if it's important.
I mean, it was going really well, and we had some extra profits. So.
Yeah. Okay. So and then here's the plug and perf depths that were based on the work that we did on the 16A to 16B crosswell fracture driven interaction picking that we did. So this, in some ways, just for terminology and vocabulary, we would call this an engineered frac, because we're not doing a geometric frac where every plug and every perforation depth is just kind of set in a sequence of equal intervals. These gun depths, these cluster depths were targeted. So we call that an engineered completion design, right? So just a little vocab there that we use in the oil industry. Most oil and gas industry plug and perf jobs are geometric type of completions. This is an engineered one. And that to a large extent, that was related to the fact that we had to TCP it. And we had limited guns and plugs. Okay, so this is just from an SPE paper a good friend of mine, Gustavo Uguieto, ex-Shell, retired now. Just some cartoons that show what we can do with in-well DAS. So if you look over here on this pie chart, the in-well DAS, we can look at stage isolation. You know, that has to do with the plug efficacy, or the cement efficacy. And I need to plug in here before I run out of juice. So with DAS, you can look at plug efficacy, and I'll show you the cartoon on that. You can also look at distribution efficiency. How well is the slurry going out of each one of the clusters? So if you look at this top case here, if you've got a stage which is sitting above the plug in this zone here, and you have, in this case, you have 5 clusters, right? This is the toe, 1, 2, 3, 4, 5. That's usually the way they're numbered. If you have a plug, if you have leakage through your plug, then you'll be retreating the stages downhill or downstream of what you really want to treat. So that's not very efficient. And that can happen from plug slippage, plug leakage, all kinds of, ways that plugs can go bad on you, to kind of not have a very efficient stage treatment. The other is that fluid can actually leak, but you might have bad cement in a zone, or you might have micro channeling. Or, you fracture, like in this case, you fractured, you're in the far field of the 16A. So there's fractures. We know there's fractures passing all through that. That can damage cement. As Kevin has alluded to, maybe there's transverse faults or fractures running up the 16B well from stage 7 to 8. Maybe that's why we have that big, huge whack and, strain feature there, which would create a leak pathway. In which case, fluid can actually leave the perforation cluster, but instead of going out into the formation, they run downhole and they retreat the old stage. So that's another problem that can happen. What you want to happen, of course, is you're pumping fluid down the well bore. It's leaving the clusters. It hits the plug and it stops. So that's a good plug hold and solid cement isolation type of job. That's what you want. That's what your objectives, of course. In this case, we don't have the far field crosswell strain monitoring because we don't have a fiber over an A. Just another cartoon, because we're using DAS here, and I haven't talked all that much about DAS. I'll just read this. So DAS and DTS enable detection of fluid movement in the wellbore through the casing perforations and in the near wellbore region. So this is a near wellbore region type of tool, not a far field type of diagnostic tool. The DAS responds to vibrations, pressure waves caused by fluid flow. Unlike the DTS, the DAS response to flow is instantaneous. So you're not relying on thermal, diffusion or anything like that. You're working off of vibrations. And as soon as fluid starts getting anywhere near a fiber, it vibrates at molecular scale. And the DAS can actually sense that and quantify it, how much vibration there is. DAS can also be used to allocate the time between clusters within a stage via the semi-quantitative empirical rate to DAS noise relationship. So this is a lot of work that Shell did over the years, and we did some of that work with them as a service provider. Okay, so actual results. What these are injection allocation logs for each one of the stages, 1, 2, 3, and 4 from the 16B pump jobs. And so we, as if I go back to this diagram here, we basically have our well bore. We have fiber on, along one side of the pipe, right? I mean, it's just running down. It's not wrapped or anything. It's just running down the pipe. But it may spiral slowly. Mm-hmm. So it's, if you think about phasing and everything, I don't know where the fiber is relative to the gun phases, you know, up, down, sideways, I don't know. But it's good at picking up all the vibrations. So the way to read these is like this. You got your pump curve data. This is your treating pressure. This is your slurry rate right here. And this is the DAS frequency band that's extracted from a 0 to 10,000 hertz acoustic recording that we made. And we segment, it's like taking an equalizer and just only looking at 128 to 512 hertz in this case, right? And that tends to show you some pretty important signal. So when you're pumping this job, you're pumping down the hole, you can see the fluid's coming down 96, 80, 97, 29. And so we know where the perfs are, right? We're told where the perforations are. And we know where the plug is in depth. So as you're pumping down, that plug is rattling. I mean, this is a ball job. This is a ball job, right? So that ball is actually sitting there in that hole, and it's rattling, it's making a lot of noise. And as the fluid exits the perforation orifices, it also generates noise. So this is perf 1, 2, 3, and 4 on that stage. And you can see that stage 1 had a lot of energy associated with it. So one way to interpret that is that there's a lot of fluid moving through port 1, more so than port 2, 3, and 4. It's kind of strange too. You see how port 2, you know, the energy kind of comes in right here, kind of starts up, but port 3 and port 4, it doesn't really start until later on. It's like there's a time lag in different clusters taking fluid and slurry, even though you're pumping, you know, from top down. Okay, so that's stage 1. Stage 2, you could see the plug down here. The plug's on here. This is really a strange period of data. See how diffuse everything looks, even in this higher frequency band. So, and I would say there's marginal plug isolation, because you see here's the plug depth, and you kind of see this energy beneath it. I mean, that plug depth is discrete in depth. So why would you happen to see fluid underneath of it? I mean, you know, I don't know. Maybe there's a little bit of fluid getting through the plug and creating some rattling underneath of it. Perf 1 definitely dominant, so that's your toward cluster. And these more hillward clusters, not very well defined. I mean, they're taking fluid early on. I mean, you're pumping in here, you're taking fluid, but they're not very discrete. Especially if you compare that to like stage 3, right? Here's stage 3. You know, here's the plug. Here's really where the plug was set. And you see this little pressure drop right here? That has meaning. I mean, you set your ball, you get this little spike in the pressure, right? You start pumping, pressure drops right there. And then all of a sudden, same time, the plug drops by, you know, I don't know, 60 feet, 50 feet. And then all that's the new plug depth. So that little bit of pressure pumping data means something. And in this case, it's the signature for a plug slip. And then perf 1, it looks like pretty crappy. You don't really see any energy along that depth. Stage 2, dominant. And then perf 3, if I'm saying stage, I mean perf. Perf 3, there's kind of diffuse energy around it, not real great, but stage 2 is dominant on that 3 cluster pump job. And then I'll just go to stage 4. We know this is the plug right here. This energy right here is the plug. And you see you get out to this point in time right here, and all of a sudden, before that, everything was quiet. It was quiet as could be underneath of the plug. Nothing was getting through. You have this little bit of a drop in the pressure, and then you get all this energy beneath the plug. So that plug is leaky or is failing. right there in time. And that completely failed because you continue to see it kind of, being evident through here, and it's pretty quiet, but there was definitely a period of time where it was leaking fluid. And that reduces your efficiency on your pump job for a period of time because you're not moving all the fluid through your perfs, you're moving them, down to the previous stage, into stage 3. So this is how you interpret DAS data for injection allocation. You can focus on the perforation clusters themselves and how the energy is distributed, or you can do plug efficacy work too. You can take this information and you can do some simple math. You can integrate over time and across a small depth window on each one of the cluster depths, and you can generate what are called injection allocation percentage maps. So this is what, using this data plus the slurry rate, the rate information, we can do a little math, and we can say this is how we estimate the fluid to be distributed in terms of what's moving through the clusters on each one of the clusters in each stage. So stage 1, I mean, this is a toe dominated stage. I mean, if we go back to this, that's that right there. I mean, the energy is dominant, right? I mean, that tells us that we think that there's more fluid moving through perf 1 than there is through perf 2, 3, and 4. So that's just quantified there. So this is the percentage of fluid allocation per cluster. So toe dominated. This stage 3 only had, and it looks like it's all going in the middle cluster. And then stage 4, the opposite of the others, it's all heel dominated. So if we go back up, here's stage 4. So there's a lot of energy, I think, tied up to when we first started pumping on it. So that's injection allocation. And there's, in this report that I'm gonna put up on the GDR, there's a lot of detail in here. Because if you think about DAS, like I said, DAS is acoustics. It measures from 0 to 10,000 hertz, or Nyquist of that is 4096 hertz. So you can slice and dice that frequency content however you want. So then we look at little frequency bands. So here's 2 to 8 hertz, 8 to 32, 32 to 128, and so on. And sometimes it's almost like you dial in to the noise. Certain frequency bands look a little bit different than others, and they give you slightly different solutions because you're using that, you're integrating the energy in there. So I don't really know how to determine what is the best frequency band to use for this kind of analysis. I don't know that. So anyways, all that detail is in here. And so that kind of covers 16B, injection allocation.
So what kind of factors would control whether it's heel or toe first and dominant?
Let me just put one caveat on all of this stuff, is that the assumption that the noise that fluid moving through a perforation orifice makes is related to the amount of fluid that goes through it, makes one big assumption. That's that the orifice shape and size doesn't change dramatically through time.
Mm-hmm.
So, through perf erosion and things like that, because you're not just pumping slick water, you're pumping slurry, it's erosive. So that can erode the perforation clusters. They know that from camera data.
Sure.
And if certain clusters erode more than others, the loss of acoustic energy could be more reflective of the perforation erosion than it is fluid allocation. So you understand what I'm saying?
Yeah.
So I'm just gonna put that out there.
Should erosion be related to the amount of fluid that goes through the perf? I would think.
Maybe. Yeah. But that's two variables all of a sudden, right? It's the volume and you're just saying maybe they're tied together. The volume is,
Say the more slurry that goes through a hole, the more eroded the hole would be.
right? So maybe we should look for no signal. I'm just saying or maybe it's the change in the signal that matters the most. So anyways, that's a qualification on the use of DAS acoustic energy for injection allocation. And nobody's really solved it yet because nobody watches perf erosion dynamically. Nobody's ever sat there and watched, okay, how does the change in the shape of a perforation cluster or hole, how does the change in that affect the acoustic energy? I mean, maybe maybe Halliburton's done it or something like that in a lab, but I'm not aware of it. So why are things why would things be heel dominated, toe dominated, or center cluster dominated? Well, I mean, the obvious answer in this case is that certain clusters are probably better connected to better fractures. I mean, we know we have fractures here.
Right.
We're not breaking new rock. We're not trying to break new rock. We're trying to get into existing fractures. So if we did a good job on targeting where those clusters were based on our previous work, then maybe those clusters that have better intake are just into good fractures. Or maybe we've just nailed a fracture, whereas the other ones, maybe we missed it by a few inches. I mean, you don't have to be off, like Maxwell Smart said, right? Missed it by this much. You don't have to miss it by much to be pumping in the granite, solid granite, and then you're trying to create a new fracture. And that's going to take a lot less fluid easily than a pre-existing fracture.
You look at the relationship between the intensity of the strain in each fracture versus the acoustic log. It seems like some fractures have strain.
That's a good piece of work that needs to be done. Right. Now relate the strain, crosswell strain to the injection allocation. Yeah. Not done yet.
Okay.
Yeah.
Hey, Dana, we had one question in the chat from Doug here. How do you differentiate between plug leakage and slippage? He's saying stages 2 and 4 seem to have similar character.
How do I differentiate between what are the two cases?
Plug leakage
Slippage
and
and
slippage.
Oh, well, yeah, I mean, if you look at the cases 2 and 4, you see how the character changes. Like this one on stage 2, you always had this acoustic energy existing below the plug depth for the entire job. From when you set the plug onward, you see how it's kind of broad versus stage, did you say stage? Okay, this is a plug slip. Was this the one, Doug, that you wanted to compare against? Or
Yeah, sorry, I had it mixed up. Stage 3 and 4, there was just that you have that step, below where the plug was set, and see that step, and it was just how do you differentiate between leakage and slippage there? I'm just curious how you're doing that.
yeah, I mean I got artistic license here a little bit, but it's interpretation. But what I see on stage 3 is that I have a defined plug. It's right there. And then at a certain moment in time, I get a pretty significant, pressure delta. And I see this coherent energy drop down. And I think that what we've done here, you see how it's quiet. I think it's pretty clear evidence that it actually moved. Do you see what I'm saying there? How you kind of your energy's here and all of a sudden it drops down.
Okay.
Yeah. Versus look
Yeah.
how different the character is here, right? I mean, you get a very small delta P on your treating pressure, and you don't really get you never really move. You still have the plug there. You see that line that I'm moving across?
Mhm.
Can you see that?
Yeah.
Yeah. And then you just have this diffuse kind of energy beneath where the plug is. And so I think this plug leak kind of healed itself. Because as you go through time, you see how it gets real quiet out here again.
Mhm.
You see that? So maybe the plug initially leaked early on in the stage, and then it plugged off with maybe proppant. Maybe just kind of
Okay,
filled
thanks.
in.
I
Yeah,
was just curious.
interpretive for sure. Okay. All right. Let me just so again, the that was 16B. I think in the essence of time, maybe what I should do, there was a circulation test.
Yeah.
Do you want to go on to
I would like to see,
the August one or the July one? Because we did one
I
right,
would like to see the latest.
the latest. Okay, let me go to the latest because that's the one, the long-term one.
Yeah, you said you had 10 days or so of
Yeah, correct.
that.
Okay, I will say to the audience here that after the 16B frac, there was a 9-hour circulation test that was done. And we have that data. But instead of going over that, what I'm going to do is jump to August and look at the circulation test that was done post 16A and 16B frac. There was a break in time, and then in the beginning of August, we started up a circulation test. So that's what this little section is on here. Acknowledge everybody. Thank you very much. Context. So this is the context of the fractures that we think exist around the producer well by virtue of the 16A frac. And then, of course, we tried to get into these same, dominant fractures during the 16B, and we pumped into those. So I'm not going to go over the whole 16B frac again, but because the 16A kind of sets up the fabric, the fracture fabric. So this is kind of an overview map of it's a waterfall plot of the RFS DSS strain change rate. And during circulation, we kind of make the assumption that there's not a lot of dynamic strain that's occurring due to fractures and stuff. It's primarily being driven by thermal changes. Remember,
Yeah.
the change in the frequency is related to both the mechanical strain change and the temperature strain change. It's both. So we make the assumption here that it's being driven by thermal type of changes. So waterfall plot 0 to the end of the fiber. The end of the fiber used to be down here. Over time, because of erosion and just the tough environment, we've lost about 100 meters of fiber by the time we ran this job. So this is well depth, MDRKB. This is time on the x-axis. These are perforation clusters from 16B. That's what I'm showing now because those are the ones that matter, right? The 16B clusters, because that's what the well is open to. And you see that pre-circulation, everything was nice and quiet. There was no strain change going on. It was a static environment. And then we opened the well up, and as soon as we opened the well up, a lot of these fractures produce big thermal anomalies for a little while, right? I mean, this is, there's an initial kind of inflow of thermal, I mean, of hot water basically, and you can see where they occur in depth and across time. And this is an overview, so I'm going to zoom into this here in a few minutes. There's certain flow signals through time, through that first day. There's some well operations that went on where they kind of had to shut in. Usually on the 16B well, they had to do some work. And when you open it back up, it affects the 16B, and you get another look at the inflow because it's like a hammer effect or something when you open it back up. So that happens various times and you get new looks at the data. And then August 11th, around 4 a.m., we had a fiber break, was diagnosed in the field, and we figured out that there was a break of some fibers in the junction box on the surface. So Wayne and I went out to the field, and Wayne did field surgery in the junction box and connected all the fibers backed up with a fusion splicer. It was amazing work, really, to kind of resurrect this thing in the field. So after this break period, you'll see that we come back live before it broke again later on downhole. Crosswell circulation test analysis. Here's the rate and pressure data. So here we got the 16A pressure data, the 16A rate, injection rate data, and the 16B pressure data. I don't have the 16B outflow rate data. I don't know if Kevin wants to mention anything about that, about availability or reliability, but maybe I didn't get it because it's not overly reliable.
So was it around August 10th that we went to 10 barrels a minute?
Yes, yes. Yes, you can see here, Joe, that, you know, here, the rate curve is this, the orange one. So we're kind of down near 0 here on August 10th, and then we kind of step up to 2.5 barrels, 5 barrels, 7.5 barrels, and then 10 barrels from August 10th through August 11th. So there's the rate rise right there in that time frame.
And we have strain data from
Yeah.
that period?
Yeah,
Okay.
yeah, I'm going to show that here. So here's now I'm zooming in to this strain rate data during the initial opening of the wells. And you can see that we've lost the very bottom of the cable up to about 9,700 feet. So we don't have a lot of inflow strain data from the first stage here. But we have all the other stages sitting above it. So red here is positive strain rate, and what that signifies is that there's hot water coming in, and it's putting a pretty good extension on the fibers in these zones right here. Here's so I'm just the various zoom ins here. I will note that there's in this data, there's a weird, you see this, how there's a change in the character in the strain data right through from here. And then there's this, it's almost like there's a cold zone right there at 9450. It's that same zone that we keep pointing out, 9450, which is at the top of stage 7 or right around stage 7. So this is stage 7 and below, stage 7 down to the, you know, end of the world. And you get above stage 7 going into stage 8, and the whole character of the inflow of the thermal response changes. And there's a cold zone that separates the two right in there. So don't be confused. I mean, you're talking about stages 7 and 8 because that's the stages from 16A. These stage numbers and clusters numbers are the stage B clusters. Yeah.
On the earlier when you were showing the that zone, that 9450
Yeah.
area, when we were talking about 16A and the perhaps leakage or something going on with 3R and then 7. One of those looked like it was showing 2 distinct, very closely spaced zones at about 9450. Do you see the same kind of in the circulation test?
Well, I don't know. I'm not sure exactly what you talk about when you look at the detail right in here. There's 2 zones right in there.
Okay.
I don't know if you see it or not, but you see that little white line here? That's real. I mean, there's a cold zone. There's a zone that's relaxing instead of expanding.
That's what you're referring to as a cold zone.
Yeah, and then there's a white line in between it. So on my screen, I can see that that's a warm zone. And then there's a cold zone above it. So I mean, this is one of the and then this is one of the beauties of high resolution. I mean, you can zoom into this and you'll be able to see that morphology pretty good. And you'll know the exact depth. Um, there's another, I mean, it's unusual too. You see this right in here, this blue streak. I mean, that's a cold fluid slug moving up the hole. You see how it's got dip on it?
Yeah.
I mean, that's cold. That's relatively cool compared to the fluid that was in and around that annulus before they opened this well. So that you'll be able to associate that exactly in depth on which cluster that's coming out of, which it looks like it's 3-1 to me, stage 3 cluster 1. And then you'll be able to associate, what frac that was associated with in that catalog, and which stage it came from before. So, and you see as you move, there's some other things in this data, like, there's you see there's a little pressure spike here there's a wellhead pressure spike on 16B, and you can see that in the whole downhole data. And again, you tend to see some repeated patterns. You see that cold slugging, that hard blue slugging moving up the hole. It's kind of coming right out of this cold zone here.
I'm confused on when this cold slug gets into the well. Like, what's the initially? What does the vertical line? Oh, it's when they change from.
Yeah,
when they start pumping.
No.
Yeah. Well, it's
We're going from 0 up to like.
Well, that's why I asked what
To
it looked like
2.1, so-
prior to August 10.
Have we done any pumping before that?
Yeah, we were
isn't that-
pumping at low volume.
well, I
Wouldn't
mean,
that be a short? Easiest to answer.
yeah. I don't think it's that far off. I mean, yeah, you're saying that if you look at the 16A pump rate curve, which is an orange here, it seems like this occurs slightly before. Is that what you mean, Clay?
Just wondering. Seems like we have a cold fluid moving through. which
Yeah, that's what I'm
could be like
saying.
a short circuit, but it also, I can tell at what stage of pumping this is, like how quickly we would have transmitted
There's no-
cooler fluid from A to B.
Well, it happens. I mean, let's just say that we're slightly off on the timing of the pumping on the 16A, which is this. What if we slid that back, right? We slid it back to that where that black line is right there. That means that feature occurs right when you put pressure onto the 16A well, onto the system. You start pushing on the system on the 16A, and almost immediately you see cold fluid, relatively cold fluid, running up the 16B well.
The instantaneous slug of cold fluid out of, I don't know where it comes from. Would that fluid have been sitting in the formation just outside of the well? I just have a hard time where this cold aliquot of fluid is coming from.
yeah.
Right at the start of the
Right,
pumping.
right. Well, as fluid,
That it only represents about a quarter of a microstrain. I mean, you just set it at relatively cold, but doesn't seem like it's just cooler than the formation than it was sitting at that time. And
yeah. Unfortunately,
we're looking at strain rates, right?
Right, this is strain rate, yes.
Yeah.
Yeah. Yeah, so it's not an absolute temperature measurement. That's right. So there's some interpretation to do more here in terms of thinking about this, the strain rate data and what these slugs mean. And I mean, certainly maybe the big picture here is that there's a big change in the character of the strain rate data in stages 1 and 2 of the 16B well versus what it looks like above that demarcation line. And why is that?
Something interesting happened at that depth, for sure.
Yeah. Now, I guess one of the things we're looking at here is we kind of took some of this data and we looked at some delay times, if that matters, right? So when we changed the rate on pumping on 16A from like 5 barrels a minute to 7.5 barrels a minute, we assume that this strain response out here, I mean, maybe that's related to the pump rate change. I mean, certainly you see a pressure spike there too on the 16B. So if you look at that delay time from the rate change, 16A, to the strain response change on 16B, it's an hour and 54 minutes. So almost 2 hours. Just something we did. I mean, I don't know if that's meaningful, but that could be transit time, how long it takes. And maybe if we did, we have various rate changes on the 16A, and if we measure the delay time over and over again, maybe it could teach us something about pathways or short circuiting. I mean, should it take, if it's not going through a short circuit, if it's just going through all the fractures, is it always an hour and 54 minutes or 2 hours? Or we see consistency there when we rate change? There was a lot happening here on the 16, not too much on the 16A pump rate. It's pretty consistent, but the 16A wellhead pressure was bouncing all over the place here. And you see, this is not just noise. You see this kind of signal over there responding in the 16B well. It needs interpretation if there's any meaning to that.
Kevin, do we have any sense of when we have refilled the reservoir?
It'll be part of the overall interpretation. Yeah, Joe. I mean, but no, I don't know where that would be at this point.
Okay, and then see what else I have in here. So anyways, I didn't have a long time to finish off this data because we just finished processing on it. But what we're trying to say here is, we definitely used fiber optics. We were able to use fiber optic sensing in the 16B well during the cross-well circulation flow testing, after the 2 wells had been stimulated and completed. In this particular case, the RFS DSS was the primary measurement being used on the single mode fiber 2 during the flow testing. I don't think we had DAS running on this during this period. And I think it provides useful information about cross-well flow and connectivity, but I just haven't done a lot of interpretation on it yet to answer some of the questions that have been brought up here. Okay, so that's what I had kind of on the circulation test so far. I think it's, and then, in the end, I don't get into it, but what happened is we kind of fixed this problem here. On August the 11th, we stayed to fix it. We got out, we started back up on the 12th, and we recorded for about another 5 days, and then we lost the fiber downhole. So we recorded through the 16th. So if there were things that happened between the 13th and the 16th in terms of well operations that could have created signal, then we got it through about the 16th before the fiber broke below about 4,200 feet. So we had a downhole failure, and that's not fixable by us right now, as far as we know. I mean, we're talking about trying to maybe fix it, but I think it's a long shot. So that doesn't do us much in terms of seeing anything in the zone of interest that we want to see. We're creative.
So given all you see, do you, and you track the cable's responses over time,
Yeah.
do you see sort of a slow degradation and then a rapid degradation just before it broke, or do you have much sense of how that cable is happening?
I mean, this is a good plot right here. If you look at this, if you look at all the signal characteristics, you know, and this is a strain change plot, right? So it's showing steady performance on the fiber optic cable for days. And then all of a sudden, it's catastrophic. I think in hindsight, when you look back, you see clues, like strange things up in, you know, that 5,000 to 4,000 foot
Yeah.
range. We've always seen it up in there. So when you look back on data, sometimes you're like, geez, I never really noticed that before. But I don't see any degradation there. And I have guys looking at this data all day, all night, trying to flag things that tell us that our equipment is working properly and the fibers are working. And nobody flagged anything. I mean, there's a little bit of a flag right here. You see this little bit of a jitter right before the catastrophic. So one of my kids works for me. He called me up like 2 o'clock in the morning. He goes, Dad, that doesn't look right. So I got in and for sure enough, it was acting weird, right? Like an hour before. And I was watching it and it just went down.
That doesn't give me enough predictive information.
Yeah, no, I didn't really see any and we do other kind of tests on the fiber. We shoot what are called OTDRs and we look at the loss profiles through time and there was nothing red flagging us. So, yeah.
Well, we should open up to questions, but I'm usually impressed
Thank you. Yeah.
now that I understand a little bit more. And you know, the value is incredible.
Just one final comment. Sometimes I talked about the zoom capabilities. This is high resolution data. We've been kind of looking at things pretty zoomed out. This is just one of the things where there was a little bit of a well operation. When you zoom in, you actually can see this slugging stuff on the strain change rate. And you see that this is time and depth, so you can measure velocities, right? Depth, time, velocities. You see how the slug velocities here are significantly different than they are here. This is slow. This fluid slug or this thermal slugging is just barely moving up the hole, real slow coming out of this zone. That just means that there's low inflow rates. This zone, it's pumping fluid. It's pumping fluid into the wellbore and it's shooting up the wellbore.
Which cluster stage?
It looks like it's probably stages kind of 2 and 3 out of, or maybe stages, 2 and 3 are pretty low rate.
Okay.
Stages 4 and 5 out of the 16 feet, they look like they're higher rate. I mean, inflow rate is related to the velocity.
Sean, are we seeing questions?
There's nothing in the box, but if anybody wanted to speak up or raise their hand, go for it. Doesn't look like it, Joe.
Okay. Well,
Let me just on the chat. Are you looking on the chat there, Sean?
yeah.
Yes, I am.
Okay.
No questions. Just Doug left a note saying thank you. This is absolutely fascinating work and a great crash course.
You know, there's a lot, like I said before, it is a versatile tool. I don't think I was overstating, you know, so there was a lot to show because, you know, you can look at everything from plug slip and plug efficiency and cluster efficiency and cross well strain, far field and fluid flow, up the well bore. And so it's a pretty broad data set that can be worked now. And I think the best research that could be done, the way to put a foundation on that is to kind of look at everything in whole. To understand what happened from cementing through circulation and everything in between, and then decide where's the outstanding questions and which part of the data set best addresses that question. That would be the way I would approach it. Because, if you have a certain question, there's definitely certain pieces that are more important than others. But in the end, I think the circulation test here is probably the most important thing. How is the well performing on flow?
Right. Well, we know it performed excellently during the circulation test.
Yeah. See, I don't know that.
Huh.
Nobody shared that with me per se.
Well, we're looking at probably 90% recovery.
Yeah.
Temperatures of what, 173 plus at the well at very good temperatures.
173?
C.
Oh, C, okay.
So good temperature.
Yeah.
Good
How much?
temperature.
About 380.
380, okay, yeah. And it was pretty consistent?
Yeah.
Right.
So very, very successful
Yeah.
test that, we're putting in 10 barrels, 400, 20 gallons a minute. Commercial, getting into better commercial range.
Yeah.
The first test was just couple barrel per hour.
That's great.
But this is minute, we're talking minute, 420 gallons a minute.
Yeah. On outflow.
Yeah. Well, inflow, but 90% recovery.
Yeah. That's great. What are your major concerns? Do you continue to do circulation tests so you can see, for 6 months to see how it performs, or, a longer period of time than 30 days? Or...
Yes. So our next, our program calls for well C. It's not designed yet, but it will, we expect hotter, deeper, a larger reservoir. Make a larger reservoir. We'll look at fluid flow through that.
That well's going to be that's a producer well?
Well, it remains to be seen whether we make it into an injector,
Yeah.
because it is deeper, it will be hotter, get some buoyancy out of this. I think, and there'll be longer term flow tests.
Yeah.
So deployment is going to be critical. I got to second what you said. Alan was essential. He did a fantastic job with you.
Yeah.
To get that cable in.
Yeah.
We've been considering expendable, but that's not the way to look at it.
No. Yeah.
Because they've all broken.
Yeah. But I think this thing provided pretty valuable information for, a significant amount of time.
And I talked to John about this question of whether it's an engineered frac, or it's just got to be geometric. And what you're kind of showing me is geometric.
For sure.
Yeah. I think if
I
you
know there's
can,
no choice. You talked about those dead zones.
yeah,
You need to get some fracture in there.
yeah. If you'd done geometric frac, you would have pissed away a lot of time and money trying to frac into that zone that had no fractures in it. Right? I don't,
Well, on the other hand, from a production point of view, you've lost surface area.
yeah.
So that's why I advocate for geometric and look for some sort of connection I don't know whether it's gonna short circuit anything.
But it could, I mean, you're only 400 feet away, and when you pumped on A, you didn't see anything in B for hundreds of feet. So if you did geometric, those would have just been dead end fractures. They would have never connected to the B well.
Well, I still think you have to frac them both geometric.
Oh, I see. And try to come
Yeah,
in from
yeah.
the other way.
Yeah, I think
Yeah.
that was clearly a lesson from
Yeah.
this is you gotta frack back.
Mm-hmm. Yeah, I mean, in terms of efficiency and long term, geometric fracks are the way to go, but that's an engineering driven decision. I don't know. I mean, I know seismic out here is crappy and everything, but I mean, in the oil industry, they have seismic.
Yeah, but they frac geometric. They
They
don't engineer their fracs.
They
just-
don't around faults. No, they don't. They'll
Yeah,
skip around faults.
You know, a fault.
Yeah,
That's
because they don't, because they don't want to waste a frac or they don't want to induce seismicity.
But we're in the same issue here. You can't see the granite. You can see the top of the granite, and we don't see any offsets on the top of the granite,
Yeah,
but we're not seeing into the granite. Although, the seismic.
I
data's
showed you the
telling us-
answer, Joe.
Yeah, the seismic data is telling us we got fractures, we know that. And even the FMI, is problematic in terms of the fracture.
Mhm. Yeah,
We don't see it in core.
Well, in Fergal, it's just fracturing geometrically.
yeah.
Yeah, they got 26
Are we still on,
pages?
are we still on the speaker here?
Yeah.
Can I just turn this speaker off here?
Yeah, we're still on.
I'm just
Okay,
hoping
well,
somebody's gonna weigh in.
If there are fracture zones or zones of weakness that you don't really know where they are, and you start stimulating into them, then you do run the risk of casing deformation and not getting into that well anymore.
Yeah, but the other risk is if you do not have enough surface area, you just do not have an economically viable production
Yes.
system.
I mean, would this be economically viable right now with the flow rates that you're getting and the temperatures?
Yeah, it's equivalent to what Fergal is doing.
Yeah, I think so.
With 4 times more clusters. So this could be viable, but I'm just speculating that I don't like those dead zones.
Yeah. Well, I mean, you could do a hybrid. I mean, you could do an engineered frac where you've got good crosswell frac signatures and you can say I could target those. And then when you get into a zone, then you just do a geometric.
If you know that in advance. Right, I mean, you won't know where your dead zones are gonna be in advance. I don't think we're good enough to predict that.
We
You
did
can't go
drill,
back in and frac between zones that you've already fracked.
No, what I'm saying is that when you frac stimulated A, and you mapped where they went on B.
Oh, well, if you have fiber, yeah, that's cool.
I thought you're always gonna have fire.
well, we're gonna have some fiber in all of the.
Come on.
Sure.
What do you think I'm over here for?
Well, long-term temperature maintenance is a critical question.
Yeah.
I think pressure shadowing is a question. I think the role of natural fractures is still an important question.
But look at Fergal, commercial scenario, they're not gonna run
The,
fiber.
um,
They got
no,
one vertical observation.
generally,
Pardon me? Well, that's a fact. Yeah.
They tried to run permanent fiber on a well here this summer. But
Yeah, that's right, yeah. So, I, unless price goes down. Or disposable fibers get proven out, I don't think they'll be using.
yeah, but let me say the way, again, just my experience in oil and gas is that absolutely nobody runs fiber on every pad and every well, certainly not. But when they run pilots, or they start,
Yeah.
you know, then they do it.
Yeah.
Because then they say, we need to learn. We're kind of at a dead end, and whatever we're doing right now isn't working so great, and we think we can improve, so let's run fiber.
Well, and that probably makes sense because these granite reservoirs are so homogeneous.
Yeah.
No, I'm being a jack.
But
But I'm just saying that I think that's the model that we try to live with, is we recognize that it's not gonna be run all the time.
Yeah.
That it's gonna be run on pilots, and then when it's run on pilots, we need to help the operators design it and run the right measurements to help them solve what they're trying to solve.
But our objectives are somewhat different, right? I mean, this is a serious research project,
Yeah,
and the information you're showing us, I don't think we'd see it
We
otherwise.
wouldn't have got it otherwise. We wouldn't have known that those fractures went in those clusters. I mean, that paid for all of the fiber.
and you wouldn't have known what, you know, you were in here, I went over the whole injection allocation stuff. You
Yeah.
wouldn't have known that there was so much variability on the injection, you know, on each one of the stages. And we haven't correlated that injection allocation response to what the fractures look like from the 16A to B well yet. Did more strain, did a better strain response lead to a better injection allocation?
And I need to get you the PLT. I don't think I've sent that to you yet.
No.
Because that's my biggest interest of the final thing to do. I mean, we don't want to burden you too much, but we have a PLT, we only got down part way. And we want to use fiber to fill in.
Yeah, I mean, if we got PLT down over some
We got,
good fiber responses, then we can at least extrapolate
we
down.
got it over 4 and 5,
Yeah.
stages 4 and stage 5
Right.
in B. Well, stage 5 wasn't pumped, but we do have data from that.
Stages 4 and 5.
And
I mean, you could, so on stages 4 and 5. I mean, here's stages 4 and 5 in the 16B. And
during the circulation.
yeah, during the August circulation. And there's definitely some inflow responses. I mean, you can actually see it kind of moving up whole here during a step rate change from 5 to 7.5 barrels a minute. So, and then we have it. I think I have one that's zoomed in. Yeah. I mean, it's. Anyways, yeah, there's more work that could be done in terms of taking the circulation period data and correlating it with PLC and looking backwards too, to see how the inflow or the circulation data correlates to the crosswell frac data.
Yeah.
Mm-hmm.
And the injection allocation data, right? I mean, from the 16B, I mean, how does that stuff relate?
And
I
there's,
don't think we have to look any further back than that, though. I think we just look at frac, crosswell frac, in-well injection allocation, and then
there's
circulation.
also some interesting tracer data.
Yeah,
Yeah, we've got
On
supporting
effectively spinner,
yeah,
tracer spinner log.
And the other thing I'd be interested in, you and I following up sometime, are the velocity of those thermal slugs going up the
Yeah.
well, and why they're so much slower than the flow rate. There must be a thermal reason for that. So Dana can map some thermal slugs apparently going up the well bore,
yeah.
and it's much slower than what the velocity of the flow is.
Yeah, we were just talking about that, so.
Well, I don't know. I mean, when you're doing it when you're pumping into a porous medium, the thermal front always lags. It's
Yeah.
1/3 of the velocity.
Yeah.
But going up the wellbore, I thought that if it's legitimately going up the wellbore, I thought it would be diagnostic of the flow rate.
We were just looking at this plot here, which is
Yeah,
during August. It's right when they opened it's when they, this. I don't know, it's early during the first day, and you can see that the flow rates.
You've got a large circle.
The mainstream of water. Pushing through the voltage. Absorption pressure. And selected. Probably it's not officially. But I'm with that. Say those slopes on that one. Kind of additive though. Would that be one?
Yeah, they are additive. Yeah, it's fluid. It is, you got. As you have fluid moving up the wellbore, it always increases up wellbore because you're adding more and more fluid to the pipe. Yes. Yeah.
So this could be, when you interpret those as 3 injection points or 3 entry points on the left-hand side,
Yeah, it could be,
difference
yeah.
in
Yeah.
fusion. So.
We have a fiber optic PLT workflow, but it usually relies on a combination of DTS temperature data
Density driven.
and velocity data from either DAS or like this. And but it's primarily driven by thermal measurements.
Well, that's true.
So,
That's.
and our Raman DTS was, the DTS fiber was going to hot by this time.
And.
Why did you hear that once? Is there, I know Solixus gave.
Sorry, there's a lot of talk in the background, guys.
Yeah.
It's hard to hear.
Try to have one conversation.
Well, I think if there are no more questions, maybe we shut the meeting down.
Yeah, I don't know, were there any more comments or questions that you guys wanted to communicate out there in the far field?
The far field?
Yeah.
You have to be stimulated.
Just.
Okay.
Oh, hey, this is no, Scott. This is Scott Butts here. No, just great work. A lot of good data. I don't have any more questions or comments. Just yeah, no, thanks for looking into all this. It's very interesting.
Yeah, hey Scott, I think one of the points here is that this data is, this data set is rich from initial cementing the fiber in place and cementing all the way through this circulation test here in August, and it provides a pretty rich data set to do a lot more work, and it'll all be available, in the public domain. So that should be a real valuable asset for researchers and students and whoever wants to use it. And the reports that'll be up with it kind of give people a grounding on what the raw data is, right? We'll associate in the reports, we'll associate what they see with where the digital data is and what it's called. So when they want to grab it, they'll know.
That's cool.
Yeah. So.
That's great.
Yeah, and I think we've, as a contractor service provider, we've learned quite a bit too, because we're not used to working in the geothermal domain at all. So it's it's helped me talk to some of the different commercial ventures that are looking at geothermal projects, and that helps me understand what their real challenges will be and whether or not fiber can help them out or not. So it's beneficial to my business in that respect because it's educated me. So
Good.
yeah,
Glad we could help you.
I mean, the only hot environment I ever worked in before was the Eagleford, and we weren't producing water. I mean, not purposefully. So thank you very much. Appreciate it.
Great.
Great.
All right.
Thanks, Dana. Appreciate you taking the time today. And as a couple others have mentioned, this was really informative and I think beneficial for the group. So thanks again. And thanks everyone for attending. We appreciate your time. Have a great rest of the day.
Thank you.
Thanks, Sean.